Look up at the night sky, and what do you see? A scattering of stars, maybe a planet or two, a faint streak of the Milky Way. But what if I told you that what you're really seeing is just the surface of something far deeper, far more connected, and almost unimaginably vast? What if every galaxy, every star, every flicker of light out there is part of an immense cosmic architecture, a hidden web of gravity, warped highways that ties the entire universe together? This isn't a fantasy or some far-off theory. This is the reality of our cosmos, a reality that's been hiding in plain sight, waiting for us to uncover its secrets. Think about it. Across billions of light years, galaxies aren't just floating alone in the dark. They're moving, shifting, influencing one another through a delicate and invisible network of gravitational pathways, cosmic filaments, and dark matter structures that form the backbone of everything we see. This is the large-scale structure of the universe, and it's one of the most profound concepts in all of astronomy. For centuries, we saw the heavens as something distant, disconnected, almost random. But today, we know better. We know that galaxies are in constant, silent conversation, linked by forces we're only beginning to understand. In this video, we're going to explore these gravity-warped highways of space, how they form, how they work, and how they've shaped the universe from its earliest moments to the present day. We'll dive into the role of dark matter, the mystery of dark energy, and the latest discoveries that are rewriting our understanding of cosmic evolution. This is a journey to the heart of one of science's greatest puzzles, and by the end, I promise you'll never look at the night sky the same way again. So settle in, open your mind, and let's explore the hidden connections that bind the cosmos together. So let's start by completely reimagining the night sky. Forget those old textbook images showing galaxies as isolated islands adrift in a vast, empty blackness. That picture is not just incomplete, it's fundamentally wrong. The true nature of our universe is one of profound connection, a magnificent architecture on the grandest possible scale. What we actually see when we look deeply enough is a cosmic web, an immense, three-dimensional network of glittering galaxy clusters, connected by long, delicate filaments of stars and gas, all woven around incomprehensibly vast, empty voids. This is the universe's large-scale structure, and it is the most important framework governing everything that happens on the cosmic stage. This idea, this web, began to take shape in the minds of cosmologists in the late 1970s and 80s. They were starting to get their first comprehensive maps of the universe from ambitious redshift surveys, which measure how fast galaxies are moving away from us. And they noticed something astonishing. The galaxies weren't scattered randomly. They were arranged in patterns, huge patterns. They formed great walls and long, river-like chains with enormous empty spaces in between. It was as if they were seeing the froth on an ocean wave or the neural connections in a brain, but on a scale of billions of light years. Cosmologist J. Richard Gott III famously compared this structure to the skeleton of the universe. Just as your bones define your shape and how you move, this cosmic skeleton defines where galaxies can live, how they grow, and where they are destined to travel. But how does a skeleton this enormous form in the first place? The story starts not long after the Big Bang itself. In those first fleeting moments, the newborn universe was not perfectly smooth. Thanks to the quantum frenzy of its birth, it was imprinted with tiny, tiny fluctuations in density. Some regions were ever so slightly denser than others. These minuscule ripples in the fabric of spacetime were the seeds of everything to come. And then gravity went to work. Over billions of years, gravity acted as the universe's great amplifier. Those slightly denser regions had a little extra gravitational pull, so they began to attract more and more matter from their surroundings. The rich got richer. The denser regions grew into vast clusters. The matter between them flowed along specific paths, forming the filaments, and the emptier regions got emptier, expanding into the great cosmic voids. It was a slow, relentless process of cosmic construction, building the web we see today. Yet, there's a profound mystery here. When astronomers added up all the gravity from the visible matter, all the stars, gas, and dust in those galaxies and filaments, it wasn't nearly enough to account for the powerful gravitational forces needed to build this web so quickly. The visible stuff we can see is just not enough. This is where the true architect, the invisible scaffolding, comes into play: dark matter. We'll explore dark matter in much more detail soon, but for now, think of it this way. The ordinary matter, the stuff that makes up you, me, and every star we see, is just the visible traffic on this cosmic highway system, but dark matter is the road itself. It's the unseen infrastructure that defines the routes. Its gravity carved out the potential wells and the pathways first, and then the regular, baryonic matter simply flowed into those pre-existing gravitational valleys, lighting up the web and making it visible to our telescopes. Our understanding of this has been supercharged by incredible technological advances. Supercomputer simulations, with names like the Millennium Simulation and Illustris TNG, allow us to rerun the history of the universe. We can input the laws of physics, add in our best estimates for dark matter and dark energy, and press play. The result is breathtaking. These simulations show the cosmic web forming in a dynamic, evolving dance, exactly matching what our telescopes eventually revealed. Meanwhile, massive observational projects like the Sloan Digital Sky Survey have painstakingly mapped the positions of millions of galaxies, literally charting the filaments and clusters in our own cosmic neighborhood. These are the maps of our universe, and they show us that these filaments aren't just pretty patterns, they are functional. They are gravitational highways, channeling vast flows of gas and entire galaxies from the barren voids toward the dense, bustling metropolises of galaxy clusters. This foundational concept of a structured, connected, and evolving cosmic web completely changes our understanding of our place in the cosmos. We are not on a lonely planet orbiting an average star in a random galaxy. We are residents of a specific point on a specific filament, in a specific supercluster, within an immense and organized cosmic architecture. But if the cosmic web is the skeleton of the universe, then we have to ask, what are the bones made of? The stunning answer is that most of this structure, this incredible architecture, is built from something we cannot see, cannot touch, and do not fully understand. It is built from dark matter. This is the invisible architect, the master sculptor whose gravity alone is powerful enough to mold the entire universe into the connected web we've begun to explore. For all its profound influence, dark matter is notoriously elusive. It doesn't emit, absorb, or reflect any light, making it completely undetectable to our telescopes. It doesn't interact with the electromagnetic force at all, so how can we possibly know it's there? The answer is written in the motion of the stars and the very shape of the cosmos. We can see what it does. We can see its gravitational hand at work. The story of this discovery is a cornerstone of modern astronomy. In the 1930s, a brilliant Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a massive gathering of thousands of galaxies. He was measuring how fast these galaxies were orbiting the cluster's center. What he found was shocking. The galaxies were moving so incredibly fast that, according to the laws of gravity, the combined mass of all the visible stars and gas in the cluster should not have been nearly enough gravity to hold the cluster together. It should have flown apart billions of years ago. Zwicky concluded there must be some form of Dunkel materie dark matter invisible mass providing the extra gravitational glue. For decades, this was seen as a curious anomaly. But then, in the 1970s, astronomer Vera Rubin provided the definitive proof. She was meticulously measuring the rotation speeds of stars within individual spiral galaxies. The expectation was that stars on the outer edges of a galaxy, far from the bright central bulge, should orbit more slowly, just as Pluto orbits the Sun more slowly than Earth. But that's not what she found. Stars on the outskirts were orbiting just as fast as those near the center. The only way this could happen is if the entire galaxy was embedded within a massive, invisible sphere of matter, a halo of dark matter that extended far beyond the visible edge of the galaxy. Her work confirmed it. As she famously said, dark matter is the gravitational glue holding galaxies together. And not just galaxies as we now know, but the entire cosmic web. So what is this stuff? We still don't know its fundamental nature, but we know what it isn't. It isn't planets, it isn't black holes made from regular matter, and it isn't clouds of cold gas. We've ruled all of that out. The leading theory is that it's a new type of elementary particle, something that hardly ever interacts with normal matter except through the force of gravity. Think of dark matter as the universe's ultimate introvert. It fills the room, it defines the shape of the room, but it refuses to talk to anyone. This aloofness is actually its most important feature. In the early universe, normal matter, the protons, neutrons, and electrons that make up everything we see, was under intense pressure. It was a hot, dense plasma that interacted constantly with light, creating a soupy, opaque fog. This pressure prevented it from clumping together easily, but dark matter, oblivious to light and pressure, was free to start collapsing under its own gravity immediately. It got a colossal head start. It began to form those tiny density fluctuations into a vast, invisible network of gravitational potential wells and valleys long before the regular matter could even begin to get its act together. This is the crucial point. The dark matter laid down the blueprint first. It created the invisible scaffolding, the underlying frame of the cosmic web. Then, and only then, did the normal, baryonic matter flow into this pre-existing structure. The gravity from the dark matter guides the gas, pulling it into the filaments and funneling it toward the intersections where galaxy clusters would eventually shine. Without this dark matter infrastructure, the force of gravity from the visible matter alone would have been far too weak to form galaxies and clusters in the age of the universe. The cosmos would be a much duller, more homogeneous, and utterly disconnected place. We owe the very existence of the cosmic web and our place within it to this mysterious substance. We can even map its distribution, not by seeing it, but by seeing its effect, through the phenomenon of gravitational lensing, where the gravity of dark matter warps the light from background galaxies, and through the incredible power of supercomputer simulations, we can trace out the ghostly contours of this invisible architecture. It defines the routes, the gravitational highways, along which galaxies have moved for billions of years and will continue to move. It dictates their fate, guiding them toward colossal collisions and mergers that will reshape them. Dark matter is the ultimate cosmic engineer, and we are only just beginning to read its blueprints. So how do we actually map this invisible dark matter scaffolding if we can't see it directly? We use one of the universe's own most ingenious tricks, a phenomenon so strange it sounds like science fiction, but is a cornerstone of modern physics. We use gravitational lensing. This is nature's own ultimate telescope, and it works by harnessing a fundamental prediction from Einstein's theory of general relativity. You see, Einstein revealed that space and time are not a static stage but a flexible fabric that can be warped and curved by the presence of mass and energy. A massive object like a galaxy or a cluster of galaxies doesn't just sit in space. It creates a dent in the very fabric of spacetime. And just as a glass lens bends light, this gravitational dent bends the path of any light traveling near it. This means that when we look at a distant galaxy, its light might not travel in a straight line to us. If there's a massive object between us and that galaxy, its gravity can act like a lens, warping, magnifying, and distorting the image we see. Theoretical physicist Kip Thorne offered a perfect analogy for this, describing it as seeing the universe through a funhouse mirror. The reflections are strange, stretched, and twisted, but if you know how to interpret the distortions, you can work backwards to understand the shape of the mirror itself. In the case of gravitational lensing, the funhouse mirror is the warped spacetime caused by dark matter, and the distorted images are our key to mapping its invisible structure. This effect comes in a few incredible flavors. There's strong lensing, which is the most dramatic. This happens when the alignment between a distant light source, a massive foreground object, and our telescope is almost perfect. The result isn't just a distortion, it's a complete transformation. We see multiple images of the same background galaxy, or stunning, luminous arcs and rings of light encircling the foreground cluster, like the Einstein ring captured in breathtaking detail by the Hubble Space Telescope. These are not physical rings of gas, they are mirages, optical illusions created by the gravity of the cluster, perfectly bending the light from a galaxy directly behind it. By studying the precise curvature of these arcs, astronomers can perform cosmic accounting. They can calculate the total mass of the cluster causing the lensing, and then subtract all the mass they can see from stars and gas. The leftover mass, which is almost always the vast majority, is the dark matter. It's the only way to weigh what we cannot see. Then there's weak lensing, which is more subtle but in many ways even more powerful. Instead of creating spectacular rings, most dark matter filaments cause a far gentler distortion. They don't create multiple images, but they do stretch and shear the shapes of thousands of background galaxies in a consistent direction, like a gentle cosmic tide. To the untrained eye, it looks like nothing, but by statistically analyzing the shapes of millions of distant galaxies, supercomputers can detect this coherent, slight stretching. It's like looking at a field of grass on a windy day. You can't see the wind itself, but you can see the direction every blade is bending. This allows us to trace the gravitational influence of not just clusters, but the vast, diffuse filaments of the cosmic web themselves. We can see how their gravity tugs on the light from more distant objects, painting a map of the dark matter highways in the sky. Finally, there's microlensing, where a smaller object like a star or a planet briefly magnifies the light of a background star as it passes in front of it. While more used for finding exoplanets, it demonstrates the universal principle at work. The power of this technique to reveal the hidden cosmos cannot be overstated. It was gravitational lensing that provided some of the first direct, albeit indirect, evidence for the existence of those dark matter filaments connecting galaxy clusters. In one landmark study, astronomers used the Hubble telescope to study a region of space between two massive clusters, Able 222 and Able 223. By meticulously mapping the subtle lensing distortions of galaxies behind this region, they didn't just find a void. They found the clear, faint signature of a filament, a bridge of dark matter stretching between the two clusters, exactly as predicted by cosmic web simulations. They were essentially weighing the road itself. Furthermore, lensing has unveiled surprises that challenge our models. some filaments appear denser and more massive than expected, while some lenses suggest that dark matter might interact with itself in ways we haven't yet predicted. It has even been used to find dark galaxies, clumps of dark matter that seem to have never accumulated enough regular gas to light up with stars. Each distorted image, each stretched arc of light, is a data point in our three-dimensional map of the invisible universe, allowing us to trace the gravitational currents that guide the fate of galaxies and finally see the hidden architecture of everything. Now let's zoom in on the very fabric of this web, the great cosmic rivers themselves, the filaments. These are not mere suggestions of structure. They are the dense, thread-like backbones of galactic connectivity, the fundamental conduits through which the universe organizes itself. Stretching for hundreds of millions of light-years, these filaments are the primary highways of the cosmos, the routes along which matter and energy flow from the barren deserts of the voids to the bustling metropolises of galaxy clusters. They are the channels that give the cosmic web its name and its function. To truly grasp their scale is a humbling exercise. A single one of these filaments can be so long that light, traveling at an unimaginable speed, would take tens of millions of years just to go from one end to the other. And within that immense span, an entire ecosystem of galactic evolution is at play. Think of them as interstellar rivers on the grandest possible scale. Just as rivers on Earth gather water from a wide watershed and channel it toward lakes and oceans, cosmic filaments gather matter, gas, dust, dark matter, and even entire galaxies from the sparse intergalactic medium and funnel it toward the dense nodes where clusters form. This flow is not gentle. It is driven by the relentless pull of gravity, carving these pathways over billions of years. The Sloan Digital Sky Survey, one of the most ambitious astronomical projects ever undertaken, has given us a profound statistic. Up to 60% of all galaxies in the observable universe reside within these filaments. They are not the exception, they are the dominant galactic environment. This means our own Milky Way is almost certainly situated within one, a part of this vast flowing current. What's truly fascinating is how dynamic these structures are. Their thickness and density are not uniform, they vary greatly, and this variation dictates their gravitational strength. Thicker, denser filaments exert a more powerful pull, acting as major superhighways that can channel immense volumes of material and influence the motion of thousands of galaxies. Thinner, more tenuous filaments are like cosmic country roads, still functional but on a more local scale. Within all of them, gravitational tides and interactions are constant. Gas clouds collide, collapse, and ignite into new stars. Galaxies passing too close to one another feel these tidal forces, which can strip away their outer layers of stars and gas or trigger massive bursts of star formation, lighting up the filament like a string of cosmic Christmas lights. This is where the seeds of galaxy growth are sown, fueled by the continuous influx of fresh gas streaming along the gravitational current. A perfect example of this immense dynamic is the Pisces Cetus supercluster filament, one of the largest known structures in our cosmic neighborhood. This colossal river of galaxies, gas, and dark matter is a perfect illustration of the filament's role as a conduit. Countless galaxies, including our own local group, are part of this flow, moving along its gravitational gradient. They are not falling randomly, they are migrating with purpose along this predefined highway, destined eventually for the great clusters that anchor the filament's endpoints. This migration is a slow, cosmic dance measured over billions of years, but it is relentless. Along the way, these galaxies exchange material. Gas is stripped from smaller galaxies and incorporated into larger ones. Dwarf galaxies are cannibalized, their stars joining the halos of giants like Andromeda and the Milky Way. This exchange is the primary mechanism of galactic growth and evolution, and it happens predominantly within the confines of these filaments. So how do these vast structures maintain the integrity of the entire cosmic web? They act as the reinforcing struts and girders. The gravitational tension within the filaments provides a counterbalance to the expansive pressure of the voids and the overarching force of dark energy. They create a stable, though dynamic, framework that prevents the universe from simply homogenizing into a featureless mist or tearing itself completely apart. They are the universe's way of creating order out of chaos, of giving form to the formless. The processes within them, the accretion of gas, the triggering of star formation, the guided migration of galaxies, are what breathe life into the cosmic skeleton, ensuring the web is not a static relic but a living, evolving structure that continues to shape the destiny of everything within it. If the cosmic filaments are the rivers and highways, then galaxy clusters are the great cities they all lead to. These are the bustling, vibrant, and often violent metropolises of the universe. Imagine a place where thousands of galaxies, each containing billions of stars, are gathered into a relatively small volume of space, all bound together by the immense gravitational pull of a single location. This is a galaxy cluster, the node where the cosmic web's grand filaments intersect and converge. They are the ultimate destinations, the gravitational anchors of the entire network. Astronomer Megan Donahue perfectly captures their importance, calling them laboratories for studying astrophysics. Within these dense communities, the most extreme and informative processes in the universe are on full display, teaching us not just about the clusters themselves, but about the fundamental forces that shaped them. The journey for a galaxy entering a cluster is a dramatic and transformative one. After flowing serenely for eons along a dark matter filament, it approaches the cluster's outskirts, where it encounters an environment unlike any other. First, it must plunge through the intracluster medium, or ICM. This is not empty space. It's a superheated, thin soup of plasma that fills the entire cluster, often reaching temperatures of tens of millions of degrees, so hot that it glows powerfully in X-rays, which our space telescopes can detect. As a galaxy rams into this seething ocean of gas at speeds of thousands of kilometers per second, it experiences a phenomenon called ram pressure stripping. It's the cosmic equivalent of sticking your hand out of a car window at high speed. The force of the wind can blow a hat right off your head. In this case, the wind of the intracluster medium can violently strip away a galaxy's own reservoir of cool gas, the very fuel it needs to form new stars. This process can effectively quench a galaxy, shutting down its star-forming factories and leaving it a red and dead relic, destined to age without creating new stellar generations. But that's just the beginning of the upheaval. The sheer gravitational chaos within a cluster subjects every galaxy to intense tidal forces. As galaxies swing past each other and the cluster's central gravitational well, these tidal pulls can stretch and distort their shapes, drawing out long, beautiful streams of stars that look like cosmic brushstrokes across the dark canvas of space. These are the telltale signs of gravitational harassment, a relentless process that can tear galaxies apart over time. And then there are the mergers. While less common in the very centers of clusters due to the high speeds of the galaxies, they do happen, especially in the outer regions or during the cluster's earlier formation. When two galaxies do collide, it's a spectacular event. Their structures are mangled, and the shock waves compressing their gas clouds can trigger ferocious bursts of new star formation, lighting up the cluster with the brilliant blue light of newborn stars. These interactions are not just for show, they are the primary drivers of galactic evolution, and clusters are the best places in the universe to observe them. To see all of this in action, we can look at a classic example, the Coma Cluster. Located about 320 million light-years away, Coma is a prototypical rich cluster, a vast collection of over 1,000 identified galaxies. In deep images, you can see them swarming together like bees, a dense cloud of stellar cities. And if we could map the dark matter, we would see the faint, ghostly tendrils of multiple filaments all feeding into this gigantic gravitational sink. Galaxies are still streaming into Coma along these pathways today, drawn in by its overwhelming pull. The cluster is a dynamic ecosystem, with giant elliptical galaxies at its heart, monsters that have grown to their immense size by cannibalizing their smaller neighbors over billions of years. The intracluster medium here is particularly hot and dense, telling us the story of countless shocks and interactions that have heated it to a frenzy. Studying Coma gives us a masterclass in how clusters evolve, how they influence their members, and how they are fed by the cosmic web. This relationship with the web is a two-way street. The clusters don't just passively receive material, they profoundly influence the entire network around them. Their immense gravity acts as the primary engine, powering the flows along the filaments. They are the vacuum cleaners of the cosmos, their pull setting matter in motion across hundreds of millions of light-years. The health and evolution of a cluster is directly tied to the vitality of its connecting filaments. A rich, massive cluster like Coma suggests a well-nourished system, with strong, active filaments constantly funneling fresh material into it. A poorer, less massive cluster might indicate weaker or depleted feeder lines. By studying the populations of galaxies within clusters, their ages, types, and motions, we can work backwards to understand the history of accretion along the cosmic highways. They are the end product of the web's gravitational flow, and by reading their story, we can understand the entire life cycle of the universe's large-scale structure, from the faintest wisp of a filament to the most crowded metropolises in the cosmos. After exploring the dense, bustling hubs of galaxy clusters, it's time to turn our gaze to the opposite end of the cosmic spectrum, the great cosmic voids. If the universe's large-scale structure is a web, then these are the enormous, empty holes in that web. They are not mere gaps or absences. They are active, dynamic regions that define the shape of the cosmos as much as the glittering filaments and clusters do. In fact, voids make up the overwhelming majority of the universe's volume. It's a humbling thought most of space is not filled with brilliant galaxies, but with vast, echoing nothingness. These voids are incomprehensibly large. While a big galaxy cluster might span 10 or 20 million light-years, a typical void can stretch for 100, even 200 million light-years across. Within that immense volume, you might find only a handful of small, isolated galaxies, like a few lone trees in an otherwise empty desert. The most famous example is the Boötes void, sometimes dramatically nicknamed the Great Nothing. Discovered in the 1980s, it is a spherical region of space roughly 330 million light-years in diameter. Yet, where astronomers might expect to find thousands of galaxies, they have only confirmed about 60. It is a staggering emptiness on a scale that challenges our imagination, but to call them truly empty is a mistake, a trick of our light-based perception. As cosmologist Laura Mersini-Horton points out, these voids are not perfect vacuums. They are filled with something, but that something is incredibly tenuous. There is a very thin soup of hydrogen gas, so diffuse it is almost undetectable. There is also dark matter, though far less concentrated than in the filaments. And perhaps most importantly, voids are filled with and dominated by the mysterious force of dark energy. This is the key to understanding their behavior. Dark energy, which causes the accelerated expansion of the universe, finds its greatest expression in these underdense regions. With so little matter to provide gravitational counterpressure, dark energy operates unimpeded, causing the voids to expand outward faster than the rest of the universe. This expansion is not a passive process. It actively shapes the entire cosmic web. Think of it as a cosmic tug of war. Inside the dense filaments and clusters, gravity is the dominant force, pulling matter inward, making structures collapse and grow denser. But inside the voids, dark energy is the champion. As a void expands, it effectively pushes against its surroundings. This creates a kind of negative pressure gradient at the boundaries between the empty voids and the dense walls of the web. Matter, both dark and visible, is effectively pushed away from the expanding void and toward the adjacent filaments. It's as if the voids are these growing bubbles, and their expansion is herding material into the cosmic roads and cities. They act as the great sculptors of the universe, their outward pressure helping to define and sharpen the very filaments they border. This dynamic creates a fascinating flow pattern for galaxies. Galaxies don't just sit still, they are in motion, and that motion is dictated by this gravitational landscape. Observations show that galaxies have a peculiar velocity, a motion on top of the universe's general expansion, that carries them away from the centers of large voids and toward the dense filaments and clusters. They are flowing downhill, away from the empty, high-pressure expanses and into the deep gravitational valleys. So, while the voids themselves may seem like barren wastelands, they are essential engines in the machinery of the cosmos. Their growth drives the continuous evolution of the web, funneling material into the pathways that will eventually build the next generation of galaxies. They are the negative space that gives the positive space its form and function, the silent, expanding backdrop against which the brilliant drama of galaxy evolution continues to unfold. Yet for all its power, dark energy remains profoundly enigmatic. We can describe what it does, but we still don't know what it is. The leading candidate is something called the cosmological constant, an energy inherent to the vacuum of space itself, first proposed by Einstein and then famously discarded by him as his greatest blunder. This concept suggests that empty space is not nothing. It has a fundamental energy density that causes it to push against itself, leading to the accelerated expansion we observe. The equation of state for this kind of dark energy is simple. Its pressure is exactly equal to minus its energy density, a relationship that remains constant over time. But is this truly the answer? Many physicists are not satisfied. The calculated value of this vacuum energy is wildly, inexplicably off from what quantum field theory predicts by a factor of 10 to the power of 120. This is arguably the worst prediction in the entire history of science, a glaring sign that our understanding is still deeply incomplete. This has led to other, more dynamic theories. Perhaps dark energy is not a constant but an evolving field, nicknamed quintessence, after the ancient Aristotelian fifth element. This hypothetical field could change in strength over time, potentially weakening or even reversing its effect in the distant future. The ongoing debate is fierce and is driven by ever more precise observational data. Missions like the Planck satellite, which mapped the cosmic microwave background in exquisite detail, and the WMAP mission before it, have provided crucial constraints. They have measured the universe's geometry and expansion history with such precision that they tell us dark energy makes up about 68% of the total energy budget of the cosmos. That's more than double the contribution of dark matter and nearly 5 times that of all the ordinary matter we can see. These observations strongly support the cosmological constant model, but they can't yet completely rule out more exotic possibilities. The quest to pin down the true nature of dark energy is one of the primary goals for next-generation observatories like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope, which will map billions of galaxies to trace the expansion history of the universe with unprecedented fidelity. So what does this mean for the cosmic web and those gravitational highways we've been exploring? Dark energy is fundamentally altering the landscape. As it accelerates the expansion, it stretches the very fabric of the cosmic web. The filaments, those great rivers of galaxies and dark matter, are being pulled ever longer and thinner. The distances between galaxy clusters are increasing at a faster and faster rate. This has a direct impact on the flow of traffic. The gravitational currents that guide galaxies along these pathways are weakening as the distances become too vast for gravity to effectively bridge. Galaxies that were once destined to eventually merge with a great cluster may now find themselves stranded, forever drifting apart as the space between them expands faster than their gravitational pull can overcome. The cosmic web is slowly being pulled taut, its connections becoming more tenuous over astronomical timescales. This leads us to the ultimate and most profound implication, the fate of the entire cosmos. If dark energy continues to behave as a cosmological constant, its relentless push will lead to what cosmologists call a big freeze or heat death. In this future, the expansion continues to accelerate indefinitely. Galaxy clusters become isolated islands, their feeder filaments stretched and broken. The space between them will expand so much that, billions upon billions of years from now, no galaxy outside our immediate local group will be visible in the sky. The universe will become a cold, dark, and lonely place. Some more speculative theories even suggest a far more violent end, the Big Rip. If dark energy were to strengthen over time, a form known as phantom energy, it could eventually overcome all forces, not just gravity. First, it would tear apart galaxy clusters, then individual galaxies, then solar systems, and finally, in a catastrophic final moment, it would rip apart atoms and the very fabric of spacetime itself. While this is considered less likely, it underscores the monumental power of this mysterious force. Dark energy isn't just another component of the universe. It is the dominant actor on the cosmic stage, holding the script that dictates the final chapter for every structure within it, from the largest supercluster down to the very atoms that make us who we are. So far, we've been talking about the invisible architects of the cosmos, the dark matter that builds the roads and the dark energy that's stretching the entire landscape. But what about the part of the universe we can actually see? This brings us to the stars of the show, quite literally, baryonic matter. This is the ordinary stuff, the atoms of hydrogen, helium, and all the heavier elements forged in stellar furnaces that make up every star, every planet, and every one of us. If the cosmic web is a vast, invisible highway system, then baryonic matter is the luminous traffic moving along it, the glowing cars and trucks that allow us to finally see the routes laid down by the dark universe. This relationship is perfectly captured by cosmologist Carlos Frenk, who explains that baryons follow the gravitational potential laid down by dark matter. Think of it like this: dark matter is the civil engineer who first surveys the land, blasts through mountains, and pours the foundational roadbed for a new interstate. But that road remains dark and empty until the asphalt crew arrives to pave it and the cars show up to use it. The baryonic matter is that asphalt and those cars. It floods into the gravitational valleys and superhighways carved out by dark matter, and it is this ordinary matter that lights up, forming the glittering galaxies and dazzling clusters that our telescopes can detect. Without this visible component, the entire cosmic web would remain utterly invisible to us, a ghostly architecture hidden in plain sight. The journey of this baryonic material is a dramatic cycle of birth, death, and rebirth. It begins as vast clouds of primordial gas, drawn into the dark matter filaments by gravity's inexorable pull. As this gas flows along the cosmic rivers, it doesn't travel smoothly. Clouds collide, creating shock waves that heat the gas to incredible temperatures. But to form stars, this gas needs to cool down. It does so by radiating away its heat energy, often in the form of ultraviolet light. As it cools, it condenses, collapsing under its own gravity into dense knots where the first stars can ignite. This isn't a peaceful process. It's a turbulent, chaotic, and spectacularly violent one. The first generation of massive stars live fast and die young, exploding as supernova within a few million years. These explosions do two crucial things. They blast newly forged heavy elements like carbon, oxygen, and iron back out into the surrounding gas, enriching it for the next generation of stars and planets, and they inject enormous energy back into the system, heating the gas and regulating further star formation. This feedback loop, also driven by powerful jets from supermassive black holes, is what governs the pace of galactic construction, preventing all the gas from collapsing into stars at once and turning the cosmic web into a single, brilliant flash. This cycling of material is a constant process. Baryonic matter is always moving between galaxies and the intergalactic medium in a great cosmic loop. A stunning example of this is happening right in our own galactic backyard, the Magellanic Stream. This is a gigantic, ribbon-like arc of hydrogen gas stretching across the sky, connecting our Milky Way to its two small satellite galaxies, the Large and Small Magellanic Cloud. This stream isn't a static bridge, it is a flow of baryonic matter in action. As these dwarf galaxies orbit the Milky Way, the gravitational tide from our galaxy is literally pulling them apart, stripping away their gas and stretching it into a long filament that trails behind them in their orbit. This stream represents fuel raw material for forming new stars. Some of this gas is already falling onto the Milky Way's disk, providing a fresh infusion of fuel that will one day collapse to form new stellar nurseries. It's a perfect nearby snapshot of the same process that fuels giant galaxies across the universe, showing how baryonic matter is channeled and redistributed along gravitational pathways. But the flow isn't governed by gravity alone. Magnetic fields, which permeate the vast spaces between galaxies, also play a crucial role in shaping this traffic. These invisible fields, thought to be amplified over time by the motion of ionized gas, can act like cosmic guardrails. They can constrain how gas clouds move, influence how they collapse, and even help channel energetic cosmic rays. While their exact origins are still a topic of intense research, their effect is tangible. They add a layer of complexity to the movement of baryonic matter, ensuring that the visible traffic on the cosmic highways doesn't just follow the simplest path, but is guided and sculpted by the universe's invisible forces, both gravitational and electromagnetic. This incredible journey begins the moment a galaxy starts to form, condensing out of the primordial gas that flows into the dark matter scaffolding. But its story is far from over at that point. In fact, that's just the beginning of a long and winding road trip across the cosmos. A galaxy's life is a product of its travels, shaped by every gravitational encounter and environmental shift it experiences along the cosmic web. Astronomer Sandra Faber's famous statement that environment is destiny for galaxies cuts to the very heart of this idea. Where a galaxy lives within the vast cosmic network, whether it's cruising down a relatively quiet filament, trapped in a dense urban cluster, or isolated in a sparse void, determines almost everything about its behavior, its appearance, and its long-term survival. We can see this dramatic environmental influence most clearly in the chaotic hearts of massive galaxy clusters. Here, the rules of galactic life are harsh and transformative. This is where we observe the Butcher-Ohmler effect, a fascinating phenomenon named after the astronomers who discovered it. They found that clusters further away, which we see as they were billions of years in the past, contain a higher proportion of blue spiral galaxies actively forming new stars. But clusters closer to us in the more recent universe are dominated by red elliptical galaxies that are largely dormant. This tells a compelling story of evolution. As galaxies are drawn into the violent environment of a cluster, their star-forming lives are effectively quenched. The mechanisms are brutal. Ram pressure from the superheated intracluster medium acts like a cosmic wind, violently stripping away a galaxy's cold gas reserves, the very fuel it needs to create new stars. At the same time, gravitational tidal forces from near misses with other galaxies can pull and distort its structure, further disrupting its delicate balance. Repeated encounters can also heat up the remaining gas, preventing it from cooling and collapsing into new stars. The result is a galaxy that slowly reddens and fades, its stellar population aging without renewal, transforming from a vibrant blue spiral into a passive red ellipse. But the story is entirely different for galaxies residing within the cosmic filaments themselves. These environments are the universe's star-forming nurseries and galactic fueling stations. Here, away from the extreme pressures of the cluster cores, galaxies can enjoy a relatively serene existence, but they are far from inactive. The filaments act as continuous conduits of fresh, cool gas, providing a steady supply of raw material for star formation. A galaxy orbiting within a filament can accrete this gas over billions of years, leading to sustained periods of star birth. This is why we often find some of the most gas-rich and actively star-forming galaxies in these filamentary environments. They are being constantly nourished by the flows along the gravitational highway. Furthermore, the lower density of galaxies in filaments means interactions are less violent and destructive than in clusters. Instead of catastrophic collisions that tear galaxies apart, they might experience gentle gravitational encounters that merely compress their gas clouds, triggering brilliant but controlled bursts of new star formation without completely destroying their structure. It's the difference between a serene countryside and a chaotic metropolis. Both have activity, but the pace and consequences are wildly different. Of course, the most dramatic events in a galaxy's life are major mergers. When two galaxies of roughly similar size collide while traveling along the same cosmic filament, it is a truly epochal event. The graceful spiral structures of both galaxies are completely shredded by immense tidal forces, their stars thrown into new, random orbits. Their central supermassive black holes eventually sink to the new center of gravity and will one day merge themselves. And all the while, the collision funnels a colossal amount of gas into the galactic center, triggering an explosive burst of star formation and often activating the black hole as a brilliant quasar. The result of this cosmic car crash is not two spirals, but a single new type of galaxy, a featureless, football-shaped elliptical galaxy. This transformation is one of the most direct pieces of evidence we have that a galaxy's morphology is not fixed at birth, but is a direct consequence of its interactions and its location within the ever-changing cosmic web. And this isn't just a remote process happening in far-off clusters, it's happening to us. Our own Milky Way is on the move, a traveler on these very same gravitational highways. Along with the entire local group of galaxies, we are being pulled by the immense collective gravity of the cosmic web towards the Great Attractor, a mysterious gravitational anomaly located in the direction of the Centaurus and Norma clusters. This motion at over 2 million kilometers per hour is our own personal experience of being channeled by the large-scale structure of the universe. Even as we speak, the Milky Way is undergoing its own evolutionary saga, having cannibalized smaller dwarf galaxies in the past and currently on a collision course with the Andromeda Galaxy billions of years from now. Our galactic fate is inextricably linked to the flows of the cosmic web. By studying the life cycles of other galaxies from their gas-rich birth in the filaments to their possible quenching in clusters or transformation in mergers, we are essentially reading our own possible futures. The cosmic web is not just a beautiful structure, it is the great stage upon which the life and death of galaxies, including our own, unfolds across billions of years. Now let's bring this cosmic journey closer to home, to a mystery that is literally pulling us through space at breathtaking speed. For decades, astronomers have known that our Milky Way galaxy is not drifting aimlessly. Along with our entire local group of galaxies, we are moving through the universe at an astonishing velocity of over 2 million kilometers per hour. But for a long time, the reason for this motion was a profound puzzle. The source of this immense gravitational pull seemed to lie in a specific direction, toward the constellations of Centaurus and Norma, but when they looked there with optical telescopes, they found nothing, or at least almost nothing. This was the beginning of the enigma known as the Great Attractor. The primary reason this region remained hidden for so long is a celestial obstacle course we call the Zone of Avoidance. This isn't some mystical barrier, it's the dusty, gas-filled plain of our own Milky Way galaxy. From our vantage point inside this galactic disk, looking toward the center of our own galaxy is like trying to see a distant city through a thick, dense fog. Countless stars and immense clouds of interstellar dust block our optical view of the universe beyond in this specific band of the sky. For centuries, this zone created a massive blind spot in our maps of the cosmos, a place where entire galaxies could hide practically in our backyard. It was within this hidden zone that the gravitational heart of the Great Attractor was beating, its presence felt only by the irresistible tug it exerted on us and thousands of other galaxies. The breakthrough in peering through this cosmic veil came not from optical light, but from wavelengths that can penetrate the dust. Infrared telescopes, like the pioneering era's satellite and later the Spitzer Space Telescope, could see the heat signatures of galaxies shining through the obscuring material. Even more powerful were radio telescopes, such as the Parkes Observatory in Australia and the Green Bank Telescope. Radio waves sail effortlessly through the dust that blocks visible light, allowing astronomers to conduct systematic surveys of this hidden realm. What they found was astonishing. They didn't find a single, monstrous object, but rather a significant overdensity of mass, a confluence of cosmic structure. As astronomer René Cron-Courtoueg's work helped reveal, the Great Attractor appears to be a massive gravitational node, likely the core of a vast supercluster where several rich filaments of the cosmic web intersect. It is this immense concentration of mass, both visible and dark, that creates the powerful gravitational sink pulling us inward. This discovery fundamentally reshaped our understanding of our local cosmic address. The Great Attractor is not our ultimate destination, but a major waypoint on a much larger journey. It is the central gravitational anchor of an even vaster structure known as the Laniakea supercluster, our home supercluster. Laniakea, a Hawaiian word meaning immeasurable heaven, encompasses over 100,000 galaxies, including our own local group, the Virgo cluster, and many others. The pull of the Great Attractor defines the primary flow within Laniakea. It is the central valley toward which all the galactic streams are flowing. Our motion is part of this grander current, a single thread in a river of galaxies all moving toward the same gravitational center. Beyond Laniakea, an even larger gravitational force, the Shapley Supercluster, exerts its own pull, meaning our journey likely continues far beyond the Great Attractor itself. So what precisely lies at the heart of this mystery? Current observations point toward the Norma Cluster, a massive gathering of galaxies, as being a central component. But the total mass required to explain the observed motion is far greater than what the Norma Cluster alone can account for. This is where dark matter once again enters the story. The leading theory suggests that the visible galaxies we can now detect are merely the tip of the iceberg, tracing out the peaks of a much larger and denser mountain of dark matter. This invisible halo is the true source of the attractor's power, a vast concentration of the universe's hidden mass that dominates the gravitational landscape of our entire supercluster. The mystery is far from solved. Ongoing efforts with more powerful infrared telescopes and sophisticated radio arrays continue to map this region in greater detail, trying to pin down the exact distribution of mass and understand the full nature of this cosmic landmark. The story of the Great Attractor is a powerful reminder that even in our own local universe, profound secrets remain hidden just out of sight, waiting for the right technology and ingenuity to reveal them. It exemplifies the relentless, dynamic pull of the cosmic web, demonstrating that even our mighty galaxy is subject to the gravitational currents of the universe, flowing along a highway whose final destination we are only beginning to comprehend. For centuries, we thought of our cosmic home as simply the Milky Way and its nearby companions, but the discovery of the Laniakea supercluster has completely rewritten that address, revealing that we are part of something far grander, a gravitational continent of staggering proportions. Laniakea, a name derived from Hawaiian meaning immeasurable heaven, is our true home in the cosmic web, a vast domain encompassing over 100,000 galaxies and stretching an almost incomprehensible 500 million light-years across. This isn't just a random grouping, it is a single, coherent river system of galaxies, all flowing under the influence of a shared gravitational landscape. The team of astronomers led by R. Brent Tully didn't discover this structure by simply drawing a bigger circle on a map. They achieved it by fundamentally changing how we measure the universe itself, moving from a static view of positions to a dynamic understanding of motion. The key to mapping Laniakea was to chart not just where galaxies are, but how they are moving. Every galaxy has two components to its motion: the general expansion of the universe, which carries everything apart, and its peculiar velocity, a unique motion caused by the local tug of gravity from surrounding structures. By meticulously measuring the velocities of thousands of galaxies, Tully's team could subtract the uniform expansion and be left with a map of these gravitational currents. What they found was breathtaking. Instead of random motion, the galaxies in our region of space were all flowing along coherent pathways, like water droplets in a vast river basin. All these streams of motion converged toward a common center of gravity, the Great Attractor region. The boundary of Laniakea is not a physical wall but a gravitational watershed, the cosmic equivalent of a continental divide. On one side of this divide, galaxies flow toward the Great Attractor and are part of Laniakea. On the other side, they flow toward a different gravitational center, belonging to a neighboring supercluster like Perseus Pisces. Within Laniakea's immense bounds, we find familiar landmarks. Our own local group, containing the Milky Way and Andromeda, is just one of many tributaries in this grand system. Major clusters like the Virgo cluster and the Hydra-Centaurus complex act as bustling hubs where these galactic rivers converge. The filaments connecting these clusters are the well-traveled highways we've been exploring, channeling the flow of galaxies and gas over hundreds of millions of years. Our entire galactic neighborhood is on a long-term journey, moving along one of these filaments toward the Norma cluster at the heart of the Great Attractor. This isn't a headlong plunge, but a gradual, inevitable flow downhill on the gravitational slope that defines our supercluster. We are not the center of this structure. We are participants in a motion that encompasses us all, a testament to the fact that gravity is the great organizer of the cosmos on the largest scales. This new understanding also redefines our relationship with our neighbors. For a long time, astronomers referred to our local supercluster as the Virgo supercluster, thinking we were merely orbiting the Virgo cluster. Laniakea shows that Virgo, while massive, is just another node within a much larger structure. We and the Virgo cluster are both flowing toward the same greater gravitational goal. Furthermore, Laniakea itself is not an isolated island. It jostles and interacts with other superclusters in the cosmic web. Its gravitational flow field juts up against that of the Perseus-Pisces supercluster, a massive wall of galaxies on the other side of our sky. Together, these structures form an even larger component of the web, a filament of superclusters that is part of the universe's grand architecture. The profound implication of Laniakea is that it makes the cosmic web tangible. It is no longer an abstract concept applied only to the distant universe. We live inside it. The same forces that shape filaments billions of light years away are shaping our own galactic journey. This discovery connects the grandest scale of the universe directly to our own local experience. It illustrates the principle that gravity is a relentless, organizing force that creates order out of chaos, gathering matter into a hierarchy of structures from the smallest clusters to the largest superclusters. Our galactic journey within Laniakea is a single thread in this immense tapestry, a slow-motion voyage that will continue for billions of years, guided by the invisible hand of gravity along the darkened highways of space. But how can we possibly test these grand theories about the universe's structure? We can't run a controlled experiment on the cosmos, and we certainly can't watch it unfold over billions of years. This is where one of the most powerful tools in modern cosmology comes into play, the ability to build a universe inside a supercomputer. Through incredibly sophisticated simulations, we can create a virtual cosmos, input the laws of physics, press play, and watch as the story of dark matter, dark energy, and the cosmic web unfolds from the first moments after the Big Bang right up to the present day. These are not mere animations, they are complex mathematical models that serve as digital laboratories, allowing us to test our understanding of the universe's fundamental rules. Some of the most famous of these virtual universes bear names like the Millennium Simulation and the Illustris TNG project. The goal of these monumental efforts is breathtakingly ambitious: to recreate the entire evolution of the large-scale structure of the universe within the memory of a supercomputer. They begin with a nearly uniform distribution of matter, seeded with the tiny, quantum-level fluctuations we see imprinted in the cosmic microwave background. Then they let the equations of gravity, hydrodynamics, and other physical forces take over. As researcher Volker Springel, a key architect of these models, has explained, these simulations allow us to test theories and predict unknown phenomena. They are the testing grounds where we can see if our ideas about dark matter and dark energy are robust enough to actually build a universe that looks like the one we observe outside our window. The process is immensely complex and requires juggling an almost unimaginable number of variables. One of the most critical ingredients is getting the initial conditions just right. These are the starting parameters of the simulation, the exact nature and amplitude of those primordial density fluctuations. If you get these wrong, the entire cosmic web that forms will not match what our telescopes see. Another huge challenge is integrating what astronomers call feedback processes. This isn't about giving the universe a performance review. It's about modeling the incredibly energetic events that regulate how galaxies form. When a massive star explodes as a supernova, it blasts out shock waves and heavy elements that heat the surrounding gas and prevent it from immediately collapsing into new stars. Similarly, supermassive black holes at the centers of galaxies can unleash tremendous jets of energy that heat gas across entire clusters, effectively shutting down star formation. Getting these feedback loops correct is essential. If a simulation doesn't include them, it will tend to form far too many small, faint galaxies and make massive galaxies far too bright, creating a universe that doesn't resemble our own. Then there's the sheer scale of the computational challenge. To model something as vast as the cosmic web, you need to simulate a volume of space large enough to contain many superclusters and voids, which means a box hundreds of millions of light-years on a side. But to see the formation of individual galaxies, you also need incredibly high resolution, the ability to zoom in on details that are just a few thousand light-years across. This creates a colossal range of scales that the simulation must handle simultaneously, pushing the limits of even our most powerful supercomputers. It's like trying to create a weather model that can predict global wind patterns while also simulating the formation of every single raindrop. Researchers have to make clever compromises, using techniques that focus computational power on dense regions where galaxies are forming and spending less effort on the empty voids. The payoff for overcoming these challenges has been nothing short of revolutionary. When we compare the universe that emerges from these simulations to the maps created by projects like the Sloan Digital Sky Survey, the match is stunning. The simulations naturally produce a cosmic web with its intricate network of filaments, its dense clusters at the intersections, and its vast, empty voids. They show how galaxies align along these filaments and flow toward the great clusters, exactly as we observe. But beyond just confirming what we already know, these digital universes have made startling predictions. They predicted, for example, that the filaments of the cosmic web should be filled with a faint, diffuse glow from shock-heated gas, a phenomenon that astronomers are now working to detect. They have also revealed the complex dynamics of how gas flows into galaxies, showing that it doesn't just fall in smoothly, but arrives in clumps and streams along the dark matter highways, fueling periods of intense star formation. These virtual explorations allow us to do something truly extraordinary. We can rewind the tape. We can trace the history of any galaxy in the simulation, from its humble beginnings as a slight overdensity in the early universe to its mature state today, understanding every merger and interaction that shaped it. We can fast forward into the future to see how the accelerating expansion driven by dark energy will eventually stretch and thin the cosmic web, isolating galaxy clusters as islands in an ever-growing void. By giving us a complete, dynamic view of the cosmos, these simulations have moved beyond mere modeling. They have become indispensable instruments for discovery, providing the virtual maps that guide our real-world telescopes toward a deeper understanding of the invisible highways that connect all things. But the cosmic web is far more than just a structure of dark matter and galaxies. It is also threaded with an immense, invisible ocean of gas. This is the Intergalactic Medium, or IGM, the tenuous plasma that fills the vast spaces between galaxies and flows along the very gravitational filaments we've been exploring. If the dark matter is the unseen roadbed of the cosmic highways, and the galaxies are the vehicles, then the IgM is the fuel and atmosphere that fills this entire system, a diffuse reservoir of primordial matter that is the true source of all future cosmic construction. This gas is almost impossibly thin. A single cubic meter of it might contain only a few atoms, a vacuum far emptier than anything we can create in our most advanced laboratories on Earth. Yet, because it permeates such an enormous volume of the universe, it contains more ordinary matter than all the stars and galaxies combined, making it the dominant form of baryonic material in the cosmos. The composition of this vast reservoir is a direct relic of the Big Bang, primarily consisting of hydrogen and helium, the original elements forged in the first few minutes of the universe's existence. But this gas is not uniform. It exists in different phases, a complex ecosystem defined by temperature and density. There is the cool IgM, with temperatures below 100,000 degrees. This gas often resides in relatively dense clouds and is detectable because it absorbs specific wavelengths of light from distant, brilliant objects like quasars, acting as a cosmic fingerprint. Then there is the warm-hot IgM, or WHIM, which is far more prevalent. Heated to temperatures between 100,000 and 10 million degrees, this gas is so energetic that it emits very faint X-rays, but is too diffuse to glow brightly, making it incredibly challenging to detect. Finally, there is the hot IgM, found in the immense spaces within and around galaxy clusters, where temperatures can soar to 100 million degrees, causing it to shine brightly in X-rays and reveal the powerful gravitational forces at work in those dense regions. This gas doesn't just sit idly in space, it is in constant motion, channeled by the gravitational pull of the dark matter filaments. This flow is the primary mechanism for galaxy growth, a process astronomers call accretion. As cosmologist Romuald Davey eloquently puts it, the IgM is the lifeblood of galaxies. Fresh, cool gas from the intergalactic medium streams along the cosmic web's filaments and spirals slowly into galaxies. Once there, it provides the essential fuel for new star formation, allowing galaxies to build new generations of stars and planets. This is a continuous cycle of cosmic nourishment. Without this steady influx of intergalactic gas, a galaxy would quickly exhaust its internal gas reserves. Star formation would sputter and halt, and the galaxy would effectively die, becoming a red and dead relic. The IgM is what keeps galaxies alive and vibrant across billions of years. But how do we possibly study something so diffuse and invisible? Astronomers have developed a brilliant technique using the universe's brightest beacons, quasars. These incredibly luminous active galaxies act like cosmic lighthouses. As their intense beam of light travels across the universe toward our telescopes, it passes through countless filaments and clouds of the intergalactic medium. Atoms within this gas absorb very specific wavelengths of that light, leaving dark, narrow lines in the quasar's spectrum, known as absorption lines. It's like analyzing the light from a distant spotlight after it has passed through a fog. The patterns in the light tell you exactly what the fog is made of. Instruments like the Cosmic Origins spectrograph on the Hubble Space Telescope are exquisitely designed for this purpose. By studying a quasar's spectrum, scientists can not only identify the composition of the intervening gas but also determine its temperature, density, and even its velocity. By observing multiple quasars in different directions, they can piece together a three-dimensional map of this gaseous web, tracing out the distribution of the IgM along the cosmic filaments that Hubble has helped to reveal. This intergalactic gas also plays a crucial role in the great cycle of cosmic recycling. When massive stars die in supernova explosions, or when powerful jets erupt from supermassive black holes, they don't just vanish. They eject enormous amounts of enriched material-heavy elements like carbon, oxygen, and iron, right back out into the intergalactic medium. This process, known as galactic feedback, seeds the pristine primordial gas with the building blocks of planets and life. This enriched gas is then swept up into the large-scale flows of the cosmic web, eventually becoming part of the reservoir that will collapse to form new galaxies and solar systems. It's a profound thought that the iron in your blood and the calcium in your bones was once forged in the heart of a dying star and then transported across millions of light years through this very intergalactic medium before eventually finding its way into the nebula that formed our Sun and Earth. The IGM is the great recycler of the cosmos, ensuring that the universe is not a static place but a dynamic, evolving system, where the death of one star contributes to the birth of future worlds, all connected by the invisible, flowing currents of the cosmic web. The cosmic web is not just a passive structure, it is a dynamic arena where galaxies engage in a continuous gravitational dance, sometimes leading to dramatic and violent encounters. Among the most spectacular of these events is a process astronomers poetically call galactic cannibalism, where larger galaxies consume their smaller neighbors in a cosmic feast that reshapes their very essence. This isn't a random act of destruction, but a fundamental mechanism of growth and evolution, driven by the relentless flow of traffic along the gravitational highways of the cosmic web. As galaxies are channeled along these filaments toward dense clusters, their paths frequently cross, setting the stage for gravitational interactions that can end in a merger, forever altering the fate of both participants. The physics behind these mergers is a complex ballet of gravity and momentum. When two galaxies draw near, their mutual gravitational attraction begins to warp their structures long before any physical collision of stars occurs. The first and most visible sign of this interaction is the creation of immense tidal forces. Much like the Moon's gravity pulls on Earth's oceans to create tides, the gravity of each galaxy tugs on the stars, gas, and dust of the other. Because galaxies are not solid objects but vast collections of loosely bound matter, these tidal pulls can stretch them, drawing out spectacular, luminous bridges and long, sweeping tails that can extend for hundreds of thousands of light years. These are not permanent structures but temporary scars of the interaction, beautiful evidence of the immense forces at play. This tidal stripping is a key part of the cannibalistic process, as it can rip material away from the smaller galaxy, transferring it to the larger one or scattering it into the intergalactic medium, where it becomes part of the cosmic web's circulating reservoir of matter. The ultimate outcome of this gravitational dance depends greatly on the size of the participants. When two galaxies of roughly equal mass collide, it is a major merger, a truly catastrophic event that forges an entirely new galaxy. The elegant spiral structures of both are completely shredded. Their stars, thrown into chaotic new orbits, no longer revolve in an orderly disk but instead form a featureless football-shaped swarm, a classic elliptical galaxy. This transformation, first demonstrated in groundbreaking computer simulations by astronomer Allard Toomer, showed how the universe can fundamentally remake a galaxy's identity through collision. But the drama isn't confined to the stars. Vast clouds of gas within the colliding galaxies are violently compressed by shock waves, triggering firestorms of new star formation so intense they are called starbursts. Meanwhile, the supermassive black holes at their centers, once dormant, are fed by this incoming torrent of gas and dust, flaring to life as brilliant active galactic nuclei before eventually sinking to the new galaxy's core and merging themselves in an event that shakes the very fabric of spacetime with gravitational waves. More common than these dramatic head-on collisions are minor mergers, where a large galaxy consumes a much smaller dwarf galaxy. This is a slower, more gradual form of cannibalism, but its effects are no less important. The smaller galaxy is gradually torn apart by tidal forces over billions of years, its stars stripped away and incorporated into the diffuse outer halo of the larger galaxy. We see evidence of this process all around us. Our own Milky Way is currently in the act of cannibalizing several small dwarf galaxies, such as the Sagittarius dwarf spheroidal galaxy, which is being stretched into a long stream of stars that wraps around our galaxy. Even more stunning is the evidence surrounding our nearest large galactic neighbor, Andromeda. Vast, faint structures of stars' tidal streams and a giant stellar halo surround Andromeda, the archaeological remnants of numerous smaller galaxies it has consumed over its long history. These stellar halos are the ghostly fossils of past meals, a record of a galaxy's growth written in the orbits of captured stars. A breathtaking example of a major merger caught in the act is a pair of galaxies known as NGC 4676, or more famously, the Mice galaxies. Located about 300 million light-years away, this system provides a perfect celestial laboratory. In stunning images from the Hubble Space Telescope, we can see the two spiral galaxies like cosmic mice, with their long, luminous tails flowing behind them. These tails are composed of millions of stars and immense quantities of gas that have been pulled out by their mutual gravitational attraction as they swing past each other. They are currently in the early stages of their interaction, destined to swing past one another several more times over the next few 100 million years before finally coalescing into a single, massive elliptical galaxy. The Mice galaxies offer us a snapshot of a process that has shaped the universe since its earliest epochs, a vivid demonstration of how the cosmic web facilitates these transformative encounters. The legacy of galactic cannibalism extends far beyond the individual galaxies involved. It is a primary engine for redistributing matter throughout the cosmic web. The gas stripped during these interactions doesn't just disappear. It is ejected into the intergalactic medium, enriching the filaments with heavy elements and providing fresh fuel that might later cool and collapse to form new generations of stars in other galaxies. This process ensures that the cosmic web is not a static map but a dynamic, recycling ecosystem. By studying these mergers, we learn more than just how galaxies grow. We learn about the flow of matter itself. They reveal the efficiency of gravity in gathering and processing material, and they show us that the majestic, isolated galaxies we see in telescope images are not islands unto themselves, but products of a long history of interaction and consumption, their current forms dictated by their journey along the gravity-warped highways of space. To truly understand the motion of galaxies, we must first grasp a fundamental duality, a kind of cosmic double life that every galaxy leads. On one hand, every galaxy is caught in what we call the Hubble flow, the relentless overall expansion of the universe itself. This is the primary motion, the grand backdrop against which everything else plays out. It's named for Edwin Hubble, whose groundbreaking work in the 1920s revealed that the universe is not static but growing, with galaxies generally receding from one another. His simple but profound law states that a galaxy's recessional velocity is proportional to its distance from us. The farther away a galaxy is, the faster it appears to be moving away. This isn't because galaxies are speeding through space away from a central point, but because the very fabric of spacetime between them is stretching, carrying them apart like raisins in a rising loaf of raisin bread. This expansion is driven by the mysterious force of dark energy, and it acts on the largest scales, defining the ultimate fate of the cosmos. But if the Hubble flow were the only force at work, the cosmic web would not exist. Galaxies would simply drift apart in a perfectly smooth, uniform manner, becoming ever more isolated in a growing void. The universe would be homogeneous and, frankly, quite dull. The reason it's not is because of the second type of motion, peculiar velocities. This term has nothing to do with being strange. In astronomy, peculiar simply means particular to itself. A galaxy's peculiar velocity is its own individual motion on top of the general Hubble flow, the deviation from that smooth expansion caused by local gravitational tugs. While dark energy pushes galaxies apart on the grandest scales, gravity is constantly pulling them together on local scales. This creates a fascinating and complex tension. A galaxy might be carried outward by the expansion of the universe while simultaneously being pulled sideways by the gravitational attraction of a nearby filament or a massive cluster. It's this combination of motions that creates the intricate choreography we see, where galaxies stream along the dark matter highways of the cosmic web while the stage beneath them is continually expanding. As researcher Mark Davis insightfully noted, peculiar velocities map the distribution of mass. This is a crucial concept. We cannot see dark matter directly, but we can see how it makes galaxies move. By carefully measuring these individual, peculiar motions, astronomers can essentially trace the invisible gravitational landscape of the universe. It's like being able to map the underwater topography of an ocean simply by observing the subtle currents and deviations in the paths of ships on the surface. Areas with a large overdensity of mass, like a massive galaxy cluster or a dense filament, will create a gravitational sink, pulling galaxies in toward it and imparting a shared peculiar velocity to all the galaxies in its neighborhood. By mapping the direction and speed of these flows, we can work backwards to find the sources of the gravity, reconstructing the architecture of the cosmic web itself, from the largest superclusters down to the finer filaments. Measuring this delicate dance requires incredibly precise observations. The primary tool for this is the redshift survey. When a galaxy moves away from us, the light waves it emits are stretched, shifting their color toward the red end of the spectrum. This redshift has two components: the cosmological redshift from the Hubble flow and a Doppler shift from the galaxy's own peculiar velocity. The challenge for astronomers is to untangle these two signals. The cosmological redshift tells us how much the universe has expanded since the light left the galaxy, which gives us its distance. The peculiar velocity is then the difference between the velocity we expect from Hubble's law at that distance and the velocity we actually measure. This requires extremely accurate distance measurements to galaxies, which is itself a monumental task relying on standard candles like certain types of supernova. By conducting these surveys for hundreds of thousands of galaxies, we can build vast maps of their velocity fields. These maps don't just show positions, they show motion. They reveal rivers of galaxies all flowing in the same direction toward a common gravitational attractor, allowing us to identify superclusters and define their boundaries, just as was done to discover our home supercluster, Laniakea. This interplay of motions perfectly illustrates the grand competition between the two dominant forces shaping our universe, dark energy and gravity. On the very largest scales, beyond the reach of even the most massive superclusters, dark energy is the undisputed champion. Its repulsive force dominates, driving the accelerated expansion and ensuring the Hubble flow is the primary motion for galaxies separated by vast voids. But on local and regional scales within the confines of the cosmic web, gravity is still in charge. Its attractive pull is powerful enough to overcome the general expansion, gathering matter into filaments and clusters and creating those all-important peculiar velocities. The cosmic web exists in the balance between these two titanic forces. It is the regions where gravity has temporarily won, creating structures of immense beauty and complexity, even as dark energy works relentlessly in the background, stretching the entire web and determining its very long-term survival. The motion of every galaxy is a testament to this ongoing struggle, a tiny data point in the grand experiment that is our evolving universe. To understand the very origins of the cosmic web, we must journey back to the universe's earliest moments, to a faint, cold glow that permeates all of space, the cosmic microwave background, or CMB. This is not just any light. It is the oldest light we can observe, the cooled remnant of the Big Bang's fiery birth, and it holds within its subtle patterns the complete blueprint for everything that would follow, including the great gravitational highways we've been exploring. Imagine taking a snapshot of the entire universe when it was a mere 380,000 years old. This is what the CMB provides. At that time, the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms, a pivotal moment known as recombination. For the first time, the universe became transparent, allowing light to travel freely across space. That light, once blazingly hot, has been stretched and cooled by the universe's expansion over 13.8 billion years, arriving at our telescopes today as a faint microwave whisper, just a few degrees above absolute zero. This background radiation is incredibly uniform, but it is not perfectly smooth. When we examine it with exquisitely sensitive instruments, we find tiny variations in its temperature, minute fluctuations on the order of 1 part in 100,000. These anisotropies, as they're called, are the most important imperfections in all of cosmology. They are the seeds from which the entire cosmic web would grow. As Nobel laureate George Smoot so perfectly described it, the CMB is the blueprint for the universe. Those tiny hot and cold spots correspond directly to regions of slightly higher and lower density in the primordial plasma. The slightly denser, hotter spots had a little more gravitational pull, and over the eons that followed, gravity acted as a cosmic amplifier, relentlessly attracting more and more matter to these spots. The rich got richer. These overdensities grew into the first dark matter halos, which then attracted baryonic gas, eventually forming the first stars and galaxies, all while the underdense regions expanded into the great cosmic voids. The entire intricate architecture of filaments, clusters, and voids was encoded in that faint, ancient light. But how did these initial density fluctuations arise in the first place? The leading theory points to a phenomenal event called cosmic inflation. This theory proposes that a fraction of a second after the Big Bang, the universe underwent an exponential, faster-than-light expansion, stretching a subatomic volume of space to something larger than the observable universe today. This violent stretching would have taken the quantum fluctuations that are inherent to empty space itself and magnified them to macroscopic scales, imprinting them as the density variations we see in the CMB. Inflation provides the elegant mechanism for creating the initial conditions, the primordial seeds that gravity would then spend billions of years cultivating into the vast cosmic web. Without this initial push, the universe might have remained far too smooth for any interesting structure to ever form. Mapping this blueprint has been the goal of several generations of space missions, each more precise than the last. The most recent and advanced of these, the European Space Agency's Planck satellite, spent years scanning the entire sky with unprecedented sensitivity. The map it produced is a Rosetta Stone for cosmologists. By analyzing the precise patterns of hot and cold spots in the CMB, scientists can extract a staggering amount of information about the universe's composition and history. The statistics of these fluctuations, their size, their distribution, their specific angular scale, are like a cosmic barcode. They allow us to measure the universe's total density with incredible precision, telling us that ordinary matter makes up only about 5% of the cosmos, dark matter about 27%, and dark energy the remaining 68%. The data tightly constrains the universe's age, its rate of expansion, and its geometry, which appears to be flat to an astonishing degree of accuracy. Every wiggle in the CMB power spectrum is a clue that helps us refine our standard model of cosmology. Perhaps most remarkably, this ancient light doesn't just tell us about the universe's ingredients, it reveals the very first stirrings of structure formation. The gravitational influence of dark matter, which had already begun to clump, left a distinct imprint on the CMB photons as they began their long journey. The patterns we see are a direct reflection of the gravitational potential wells that dark matter was already creating, the very wells that would eventually guide baryonic matter into the filaments and nodes of the web. By comparing the statistical properties of the CMB fluctuations with the large-scale structure we see in the universe today, we can trace a direct evolutionary line. The same statistical signature present in the distribution of galaxies across billions of light-years is already there in nascent form in the infant universe's first light. It confirms that the cosmic web didn't form randomly but grew in a predictable way from a specific set of initial conditions. The secrets held within this microwave echo are far from exhausted. Future experiments will probe it for even fainter patterns, like the faint twisting of light's polarization that could provide evidence for gravitational waves from the epoch of inflation, a discovery that would take us even closer to the very beginning of everything. The CMB is our most direct window into the primordial universe, a fossilized snapshot that captures the moment the cosmic dice were rolled. It shows us that the fate of the cosmos was not random but was set on its course by the initial, microscopic wrinkles in spacetime, the gravitational seeds from which all structure and ultimately ourselves would grow. Now let's turn our attention to the most brilliant beacons in the cosmos, objects so luminous they can outshine entire galaxies, yet are powered by a source smaller than our solar system. These are quasars and their kin, known collectively as active galactic nuclei, and they serve as our most powerful flashlights for illuminating the darkest, most distant stretches of the cosmic web. At the heart of these phenomenal objects lies a supermassive black hole, but not a dormant one. This is a black hole in the act of feasting, consuming vast quantities of gas and dust that have been channeled directly to its doorstep by the gravitational currents of the cosmic filaments. As this material spirals inward at nearly the speed of light, it forms a searingly hot accretion disk, converting immense amounts of gravitational energy into light with unbelievable efficiency, making these objects visible across the universe. The story of their discovery is a classic tale of scientific curiosity. In the early 1960s, astronomer Martin Schmidt was studying what appeared to be a faint, blue star catalogued as 3C273. Its spectrum was baffling. It contained emission lines that didn't correspond to any known element. Schmidt had a revolutionary realization. The lines were from common hydrogen, but they were shifted so far toward the red end of the spectrum that the object had to be moving away from us at a staggering 16% of the speed of light, placing it billions of light years away. For something that distant to appear so bright in our telescopes, it had to be emitting hundreds of times more energy than our entire Milky Way galaxy. He had discovered the first quasar, short for quasi-stellar radio source, and in doing so, he gave us what he would later call cosmic lighthouses, distant, brilliant beacons whose light could be used to probe everything between them and us. Their incredible luminosity is not just for show, it is the direct result of their prime location within the cosmic web. quasars and other active galactic nuclei are not scattered randomly. They are found preferentially at the busy intersections of cosmic filaments, the nodal points where the gravitational highways converge and the flow of intergalactic gas is most abundant. This is no coincidence. It is at these intersections that the dark matter density is highest, creating the deepest gravitational wells that efficiently funnel vast reservoirs of gas toward the central black hole. The supermassive black hole acts as the ultimate engine, but the cosmic web provides the fuel supply. The same filaments that guide galaxies also channel a continuous stream of gas, ensuring the black hole has plenty of material to consume, powering an outburst that can last for millions of years. This makes these active nuclei perfect tracers for the underlying architecture of the web. Where we find a quasar, we are almost certainly looking at a dense knot in the cosmic network. Beyond merely marking these locations, the light from quasars acts as a powerful diagnostic tool. As their brilliant beam travels across the universe toward Earth, it passes through the tenuous gas that permeates the cosmic filaments. Atoms within this gas absorb specific wavelengths of the quasar's light, creating a unique absorption line fingerprint in its spectrum. By analyzing these absorption lines, astronomers can determine the composition, temperature, density, and velocity of the invisible gas clouds that the light passed through. It's like analyzing the spectrum of a distant spotlight after it has passed through a fog. The patterns in the light tell you exactly what the fog is made of. This technique, using thousands of quasars, has allowed us to create detailed three-dimensional maps of the distribution of ordinary matter in the cosmic web, revealing the vast reservoirs of warm hot gas that would otherwise be completely undetectable. However, the influence of these active galactic nuclei is not a one-way street. They don't just passively trace the web, they actively reshape it through powerful feedback processes. When a supermassive black hole is actively feeding, it doesn't consume all the material that falls toward it. Some of the gas is magnetically funneled away from the poles at near light speed, launching colossal jets that can extend for hundreds of thousands of light years. These jets punch through the host galaxy and inject enormous amounts of energy and momentum into the surrounding intergalactic medium. This has a profound regulatory effect. By heating the surrounding gas, these outflows can prevent it from cooling and collapsing to form new stars, effectively quenching star formation in the host galaxy and its neighbors. This feedback mechanism is a crucial component of galaxy evolution models, explaining why the most massive galaxies in the universe are often red and dead with little ongoing star formation. The black hole, fueled by the cosmic web, eventually acts to shut down the very processes that built its home. A prime example of this incredible power is the very first quasar discovered, 3C273. Despite being located over 2 billion light-years away, it remains one of the brightest quasars in our sky. Observations reveal not only its brilliant core, but also a spectacular jet stretching across thousands of light-years. Studying this jet helps us understand how energy is transferred from the black hole into the surrounding environment, influencing the evolution of the entire galactic cluster it resides in. It serves as a nearby laboratory for studying the complex relationship between a supermassive black hole, its host galaxy, and the larger cosmic structures that feed it. By observing such beacons, we gain a clearer picture of how the cosmic web functions not just as a static map, but as a dynamic system where energy and matter are continuously exchanged, shaping the fate of galaxies across the breadth of the universe. But this grand cosmic architecture we've been exploring, this magnificent web of interconnected galaxies and dark matter highways, is not a permanent fixture of the universe. It exists in a delicate and temporary balance between two titanic forces, the relentless inward pull of gravity and the mysterious outward push of dark energy. And right now, the scales are tipping decisively. The fate of the cosmic web is one of gradual and then accelerating dissolution. The very connectivity that defines the universe today will, over astronomical timescales, be stretched and pulled apart. We are living in what cosmologists call the stelliferous era, the age of stars, a period of vibrant structure and brilliant light. But this era will not last forever. The future that awaits is one of increasing isolation, darkness, and a profound silence. To understand this future, we need to focus on the engine driving it, dark energy. This enigmatic force, which makes up about 68% of the universe's energy content, acts as a kind of anti-gravity, causing the expansion of space itself to accelerate. This isn't just galaxies moving apart from each other. It's the very fabric of spacetime between them growing larger at a faster and faster rate. The immediate effect on the cosmic web is to stretch it. Those great filaments, the cosmic rivers that channel galaxies and gas, will be pulled ever longer and thinner. The gravitational currents that flow along them will weaken as the distances between mass concentrations become too vast for gravity to effectively bridge. Galaxy clusters, those bustling metropolises, will become more and more isolated. They will continue to grow through mergers for a time, vacuuming up the last galaxies flowing along the fading filaments, but eventually even that inflow will cease. The clusters will become isolated islands in an ever-growing sea of nothingness. This leads us to a future scenario that cosmologist Lawrence Krauss has vividly described, where galaxies become islands in an ever-growing void, slowly losing all their cosmic linkages. This is the heat death or big freeze scenario. In this future, the expansion continues indefinitely. Billions of years from now, an astronomer in the Milky Way, assuming it has long since merged with Andromeda, would look out into a profoundly dark sky. All other galaxy clusters, carried away by the accelerating expansion, would have been redshifted beyond the visible horizon. Their light, stretched to wavelengths longer than the size of the observable universe itself, would simply never reach us. The universe would appear as a single, giant galaxy adrift in an absolute blackness, with no external clues to suggest there had ever been anything else. Star formation would eventually cease as all the interstellar gas is either used up or ejected, and the remaining stars would burn out one by one, leaving behind a cold cosmos of black holes, neutron stars, and dead stellar embers slowly drifting apart. The timeline for this dissolution is almost unimaginably long, but cosmologists can project it using our knowledge of physics. For the next several tens of billions of years, the cosmic web will remain largely intact, though increasingly strained. Galaxies within bound clusters like Virgo or Coma will remain gravitationally tied to one another, as their local gravity is strong enough to resist the global expansion. The real unraveling will happen on the larger scales. The filaments connecting these clusters will be the first to go, stretched and severed by the accelerating expansion. Over hundreds of billions of years, even the clusters themselves may begin to feel the strain if dark energy behaves in certain ways. The exact timeline hinges critically on the true nature of dark energy, specifically its equation of state, the relationship between its pressure and density. If dark energy is a true cosmological constant, as Einstein proposed, its strength will remain steady, leading to the long, slow freeze we just described. This is the most widely accepted model based on current data. However, there exists a more speculative, far more violent alternative, the Big Rip. This scenario arises if dark energy is not constant, but is instead a form of phantom energy that grows stronger over time. In this model, the repulsive force of dark energy would not only accelerate the expansion, but would itself increase in intensity as space expands. This would create a runaway feedback loop. First, the phantom energy would overcome the gravitational bonds holding superclusters together, tearing apart the large-scale structure. Then it would rip apart individual galaxy clusters. As the force continues to strengthen, it would tear galaxies apart, then solar systems, and then, in a final, catastrophic moment, it would overcome the forces holding atoms and even atomic nuclei together, shredding the very fabric of spacetime itself in a singular, apocalyptic instant. While the Big Rip is considered a less likely possibility given current observations, its existence as a theoretical outcome reminds us of the truly awesome and unpredictable power of the force that now dominates our universe's evolution. This outlook forces us to confront profound questions about the nature of our cosmos and our place within it. The gravity-warped highways have been the great facilitators of galactic evolution, driving growth, triggering star formation, and building the complex structures we see today. But in a future dominated by dark energy, that evolution will effectively cease. The flow of gas along the filaments will stop, starving galaxies of the fuel they need to make new stars. Galactic collisions and mergers, the great engines of change, will become impossible as the distances between all structures become unbridgeable. The universe will transition from a dynamic, evolving system to a static, frozen one. The cosmic web, which has given the universe its rich texture and interconnected history, will fade into memory, leaving behind a cosmos that is increasingly empty, silent, and alone. It's a humbling reminder that the vibrant, connected universe we see today is a fleeting phase in a much longer and more austere cosmic story, a brilliant but temporary flash of structure in the vast dark. Mapping the invisible structure of the cosmos requires a kind of astronomical detective work, a multi-pronged investigation that uses every tool at our disposal to trace the faint outlines of the dark matter web. This isn't a single method endeavor, it's a symphony of complementary techniques, each instrument playing a different part to reveal the full score of the cosmic symphony. Astronomers like Daniel Eisenstein emphasize that multi-messenger astronomy is key because no single observation can tell the whole story. The dark matter filaments themselves are completely black, and the gas within them is often too thin to glow brightly. So we must be clever, piecing together the puzzle by observing how this hidden structure influences the things we can see, the light from galaxies, the distortion of space-time, and the faint whisper of radio waves from the depths of space. It all begins with the most fundamental map-making tool, the redshift survey. This technique provides the three-dimensional atlas of the visible universe. By measuring the redshift of a galaxy, how much its light is stretched to longer wavelengths by the expansion of the universe, astronomers can calculate its distance from us. When you painstakingly measure the redshifts of hundreds of thousands, even millions of galaxies, you can plot their positions in space. Projects like the Sloan Digital Sky Survey did exactly this, and the resulting maps were revolutionary. They didn't show a random scatter, they revealed the vast cosmic web in stunning detail, with galaxies lining up along intricate filaments and clustering at their intersections. This was our first direct visual evidence of the large-scale structure, the luminous traffic tracing out the invisible roadways. But this map only shows us where the galaxies are. It doesn't directly show us the dark matter between them or the thin gas that fills the voids. To find that missing material, we turn to a more subtle probe, the Lyman Alpha Forest. This beautifully named phenomenon involves using the brightest objects in the universe, quasars, as cosmic flashlights. As a quasar's incredibly powerful beam of light travels across billions of light years to reach us, It passes through countless clouds of neutral hydrogen gas that float within and between the cosmic filaments. These clouds absorb very specific wavelengths of the quasar's light, imprinting a unique fingerprint on its spectrum. The result isn't a single absorption line, but a whole forest of them, each line corresponding to a different hydrogen cloud at a different distance. By decoding this forest, astronomers can do more than just confirm the gas is there. They can determine its temperature, density, and crucially, its velocity. This allows us to map the intricate flows of gas along the filaments, revealing how this raw material is channeled from the voids toward the hungry galaxies and clusters, effectively charting the currents within the invisible rivers. For the hottest components of the web, we shift our gaze to the high-energy end of the spectrum. X-ray telescopes like the Chandra X-ray Observatory are essential for detecting the seething plasma that is caught in the gravitational grip of massive filaments. When vast flows of gas are funneled into the deep potential wells of the cosmic web, they can collide and create powerful shock waves. These shocks heat the gas to temperatures of millions of degrees, causing it to glow not in visible light but in X-rays. While this emission is incredibly faint, it is detectable. A landmark discovery came from studying the space between two clusters, Able 222 and Able 223. X-ray observations revealed a faint but definite bridge of million-degree gas connecting them, the first direct imaging of the hot gas within a cosmic filament, confirming that these structures are not just theoretical but tangible, physical conduits of matter and energy. Meanwhile, radio telescopes offer a completely different window into this hidden world. Their great strength is detecting the signature of cold, neutral hydrogen gas, the primary fuel for star formation. This gas emits a characteristic radio wave with a wavelength of 21 centimeters. By tuning their massive dishes to this frequency, radio astronomers can map the distribution of this primordial hydrogen throughout space. This allows them to find gas that is too cold to emit X-rays and too diffuse to absorb light prominently, filling in a critical gap in our understanding. Projects like the upcoming Square Kilometer Array Observatory promise to revolutionize this field, with the sensitivity to map the cosmic web in hydrogen alone, potentially tracing the faintest and most distant filaments back to the dawn of cosmic time. And underpinning all of these methods is the powerful technique of gravitational lensing, which we discussed earlier. It remains the only way to directly map the total mass, the dark matter itself, independent of its temperature or whether it's associated with visible galaxies or glowing gas. By measuring the subtle distortions of background galaxies caused by the gravity of a filament, we can literally weigh the structure and create a profile of its density. This provides the crucial confirmation that the patterns we see in galaxy surveys, the gas we detect in X-rays and radio waves, are all flowing along a backbone of invisible matter. The true power is unleashed when these techniques are combined. A gravitational lensing map can show the mass of a filament. An X-ray observation can show its hot gas. A Lyman alpha forest analysis can show the kinematics of its cooler gas, and a redshift survey shows the galaxies riding along its length. Together, they provide a complete picture, a multi-wavelength confirmation that these gravity-warped highways are real, dynamic, and essential to the story of our structured universe. For decades, cosmologists have been faced with a deeply puzzling accounting error on the grandest possible scale. When they calculated the total amount of ordinary matter, the protons, neutrons, and electrons that make up everything we can see, from stars and planets to our own bodies, that should have been created in the Big Bang, the numbers were very precise. Yet, when they added up all the ordinary matter they could actually observe in the present-day universe, locked within stars, galaxies, and even the hot gas in galaxy clusters, they came up short. A huge portion, roughly 30 to 40% of all the baryons that should exist, was simply missing. This was the infamous missing baryon problem, a glaring gap in our inventory of the cosmos that suggested we were fundamentally misunderstanding where and how matter resides. The solution to this cosmic mystery, it turns out, was hiding in plain sight, or more accurately, in the emptiest places. Astronomers now believe they have found the universe's missing matter, and it's not in some exotic, unknown form. It's exactly where it should be, in the spaces between the galaxies, but it's not in a state we could easily see. This missing material is thought to be spread throughout the cosmic web in the form of an incredibly diffuse, superheated gas known as the warm-hot intergalactic medium, or WIM. As astrophysicist Fabrizio Nicastro has stated, the cosmic web hides the universe's missing matter. This tenuous plasma, with temperatures ranging from 100,000 to 10 million degrees, is simply too hot and too thin to emit light brightly enough for our telescopes to detect with traditional methods. It's the equivalent of trying to see the faint, heat-induced shimmer above a desert highway from thousands of miles away. The signal is there, but it's incredibly weak and easily lost against the background. So how did this primordial gas get so hot? The story is one of violence and motion on a cosmic scale. As gravity pulled matter into the filaments and nodes of the cosmic web over billions of years, it wasn't a gentle process. Vast rivers of gas flowing along the dark matter highways often collided with each other or slammed into the dense gas already gathered in galaxy clusters. These collisions created immense shock waves, similar to the sonic boom from a supersonic jet, but on a scale of millions of light years. These shocks did to the gas what pumping air into a bicycle tire does. They compressed it and, in doing so, heated it to tremendous temperatures. This process, known as shock heating, effectively took the cool, pristine hydrogen and helium left over from the Big Bang and cooked it into a thin, hot soup that permeates the entire cosmic web. It's this same process that heats the gas in galaxy clusters to glow in X-rays, but in the filaments, the WIM is far more diffuse, making it the ultimate challenge to observe. This is where the cosmic filaments play their crucial role as reservoirs. They are not just pathways for galaxies, they are the storage tanks for the universe's missing baryons. The gravitational pull of the dark matter within a filament is strong enough to hold onto this hot gas, preventing it from simply dissipating into the even emptier voids. Think of the filament as a wide, shallow river valley. The water in the river is the galaxies and the cooler, denser gas we can see, but the entire valley is filled with a thick, hot fog, the WIM, that is an integral part of the system, even though it's much harder to perceive. This realization fundamentally ties the existence and structure of the cosmic web to one of cosmology's most basic questions: where is all the stuff? The answer is that it's woven into the very fabric of the universe's large-scale structure, a gaseous component of the web that contains more ordinary matter than all the stars in all the galaxies combined. Finding this ghostly material has required extraordinary ingenuity and some of the most advanced telescopes ever built. Since the WIM is too faint to see directly, astronomers again use quasars as distant flashlights. When the intense light of a quasar passes through a filament of the WIM, the superheated gas imprints its signature on the light. Atoms of oxygen and other heavy elements within the WIM, which were forged in early stars and spread by supernova, absorb very specific wavelengths of ultraviolet and X-ray light. By analyzing the quasar spectrum with powerful instruments like the Cosmic Origins spectrograph on the Hubble Space Telescope and X-ray observatories like Chandra and XMM Newton, researchers can hunt for these extremely faint absorption lines. It's a painstaking process, like trying to find the unique chemical signature of a few specific molecules in a vast ocean by analyzing a single beam of light that has passed through it. But slowly, success is coming. There have been several tantalizing detections, including a famous study of a quasar called H2-356-309, where astronomers finally found the long-sought spectral fingerprints of oxygen in the WIM, confirming the presence of this massive reservoir of baryons in the cosmic web. This discovery does more than just solve an accounting problem. It profoundly deepens our understanding of galactic connectivity. The WIM isn't just hiding between the galaxies, it is the medium through which they are connected. This hot, diffuse gas is the primary evidence that the cosmic web is a continuous physical structure, not just a map of gravitational points. It shows that the space between galaxies is not truly empty, but is filled with a tangible, if ethereal, substance that links all structures together. Furthermore, this reservoir plays a dynamic role in the life cycle of galaxies. While much of the WIM is too hot to directly collapse and form stars, simulations suggest that clumps of it can cool over time, providing a slow but steady trickle of fresh fuel that can fall onto galaxies, potentially reigniting star formation in otherwise quiescent systems. The ongoing effort to map this material is therefore about more than just completing a census. It's about understanding the complete ecosystem of the universe, from the hottest, most diffuse gas in the filaments to the coldest, densest clouds giving birth to new stars. In finding the missing baryons, we haven't just solved a mystery, we have filled in the missing links of the cosmic web, revealing it to be a vast, dynamic, and tangible network that truly connects all things. Yet as we map the grand flows of dark matter and the vast rivers of hot gas, there is another, even more elusive force at work within the cosmic web, a silent, invisible influence that guides and sculpts the traffic moving along the gravitational highways. We've been thinking of these pathways in terms of mass and gravity, but the universe is also laced with another fundamental force, magnetism. Incredibly, magnetic fields permeate the voids, thread through the filaments, and wrap around entire galaxy clusters. They are a ghostly presence, an unseen layer of structure that adds a whole new dimension of complexity to how the cosmic web functions. While their strengths are often faint, their cumulative effect can be profound, influencing everything from the collapse of gas clouds to the acceleration of particles to near light speed, acting as a subtle but persistent guide on the cosmic journey of matter. The very existence of these vast magnetic fields is a deep cosmological puzzle. How do you magnetize the entire universe? The leading theories suggest the seeds for these fields were planted in the universe's infancy. Tiny magnetic fields could have been generated in the violent turbulence of the primordial plasma, just moments after the Big Bang. Alternatively, they might have been born from the intense outbursts of the first stars and galaxies, spewed out into the intergalactic medium by powerful supernova winds and jets from active black holes. Once these weak seed fields were in place, a process known as a dynamo effect took over. As clouds of ionized gas plasma moved through the universe, their motion could stretch, twist, and amplify these initial magnetic fields, much like a turbine generates electricity here on Earth. This amplification is supercharged by turbulence, the chaotic, violent motions within galaxies and within the large-scale flows of the cosmic web itself can tangle and intensify magnetic fields, building them up from incredibly weak beginnings to the strengths we can now detect. Detecting them, however, remains a monumental challenge. We cannot see magnetic fields directly. Instead, we observe their effects. The primary tool for this is the radio telescope. When high-energy electrons, often accelerated by shock waves in the cosmic web, spiral around magnetic field lines, they emit a very specific type of radio wave known as synchrotron radiation. This emission acts like a tracer, painting the invisible magnetic fields in light we can see. Furthermore, the orientation of the light waves from distant radio sources can be slightly rotated as they pass through magnetized plasma, an effect known as Faraday rotation. By meticulously measuring this rotation, astronomers can work backwards to map both the strength and the direction of the magnetic fields that caused it. It is through these subtle, indirect techniques that we've begun to appreciate that magnetism is not confined to galaxies, but is a fundamental property of the intergalactic medium itself, a hidden component of the universe's large-scale structure, as researcher Ellen Zweibel has described. So what do these fields actually do? Their influence is often subtle but pervasive. Within the cosmic filaments, magnetic fields can act as a kind of cosmic scaffolding for the gas flowing along them. The fields provide pressure and tension that can help support clouds of gas against gravitational collapse, potentially slowing down the process of star formation or channeling it into specific areas. They can also prevent the hot, diffuse gas within filaments from dissipating too quickly, helping to maintain the integrity of these vast structures over billions of years. Perhaps their most dramatic role is in the acceleration and guidance of cosmic rays. These high-energy particles, primarily protons and electrons, are thought to be accelerated to incredible speeds by shock waves within the cosmic web. The magnetic fields then act like the rails of a particle accelerator, confining these rays and guiding them along the filaments, sometimes for millions of light years, before they finally escape or collide with something. This makes the cosmic web not just a structure of matter, but a vast, interconnected network for transporting energy across the universe. A stunning example of magnetic fields shaping a galactic environment can be found much closer to home in the heart of the Virgo cluster. This dense gathering of galaxies is not only filled with hot X-ray emitting gas, but is also permeated by a large-scale magnetic field. Radio telescope observations reveal faint but extensive lobes and filaments of synchrotron emission, tracing out the magnetic field lines that are woven through the intracluster medium. These fields are thought to play a crucial role in the cluster's ecosystem. They can help regulate the transport of heat, potentially preventing the central regions from cooling too rapidly. They also influence the spectacular tails of gas that are stripped from galaxies as they plunge through the cluster, shaping these streams and affecting how the stripped material is eventually recycled back into the intracluster medium. The Virgo cluster shows us that to understand the physics of these dense environments, we cannot ignore the magnetic force. It is an integral player in the dynamics. One of the most intriguing and unresolved questions is how these magnetic fields might interact with the dominant component of the cosmic web, dark matter. Dark matter, as far as we know, does not interact with electromagnetic forces at all. It should be completely oblivious to magnetic fields, and magnetic fields, being a property of the ionized plasma, should be entirely confined to the ordinary baryonic matter. Yet, they both occupy the same space and influence the same gas flows. The gravitational pull of dark matter dictates where the gas flows, and the magnetic fields within that gas can then influence how it behaves once it gets there. It's a one-way interaction, but a critical one. The presence of magnetic fields could alter the rate at which gas cools and condenses to form stars within the dark matter halos of galaxies, subtly influencing the entire process of structure formation. Understanding this interplay is a frontier of astrophysics, a reminder that the universe is a complex system where multiple forces, both known and hidden, work in concert to build the reality we observe. But the influence of these supermassive black holes extends far beyond their immediate neighborhood. Their gravitational reach is so immense that during close encounters between galaxies, the black holes themselves can act as gravitational anchors, subtly deflecting the paths of entire stellar systems. The pioneering work of astronomer Andrea Ghez, who confirmed the existence of the supermassive black hole at the center of our own Milky Way, underscores their sheer gravitational dominance. When two galaxies pass near one another on their journey along a cosmic filament, it's not just the collective gravity of their stars that dictates the interaction. The supermassive black holes at their cores exert a powerful, localized pull that can significantly alter the trajectories of the passing galaxies, much like a massive planet bending the path of a comet. This gravitational steering can determine whether two galaxies continue on their way, become locked in a long-term dance, or are flung on entirely new courses within the cosmic web, effectively rerouting galactic traffic on a grand scale. The most dramatic display of a black hole's influence, however, occurs when two galaxies do not just pass by but actually merge. When galaxies collide, their central black holes eventually sink to the new common center of gravity through a process called dynamical friction. As they spiral inward over millions of years, they form a binary pair, whirling around each other in a frantic dance. This binary black hole system creates a complex and shifting gravitational field that can violently stir up the surrounding stars and gas, throwing them into new orbits and further reshaping the newly merged galaxy. The eventual merger of the two black holes themselves is a cataclysmic event, releasing a stupendous burst of energy in the form of gravitational waves that ripple through the very fabric of spacetime. This final kick from the merger can even eject the resulting single black hole from the center of the galaxy at high speed, a gravitational recoil that would leave the galaxy without its central anchor, sending it on a new and unpredictable trajectory through the cosmic web. Beyond their raw gravity, active black holes exert a second, more pervasive form of control through their phenomenal energetic output. When a supermassive black hole is actively feeding on infalling gas, it doesn't quietly consume all the material. Instead, it can convert a significant portion of the gravitational energy into intense radiation and channel some of the matter into colossal, magnetically driven jets that shoot out from its poles at nearly the speed of light. These jets can extend for hundreds of thousands of light years, far beyond the boundaries of their host galaxy, punching directly into the intergalactic environment of the cosmic web. Simultaneously, powerful winds of hot gas are blown outward from the accretion disk. This dual-pronged assault of jets and winds injects a colossal amount of energy and momentum into the surrounding gas, both within the galaxy and in the intracluster medium. This process, known as active galactic nucleus feedback, is a crucial regulatory mechanism. By violently heating the surrounding gas, the black hole prevents it from cooling down and collapsing to form new stars. It's a self-regulating cycle. The same inflow of gas that feeds the black hole and allows it to grow also powers the feedback that eventually shuts down the fuel supply, quenching star formation and effectively putting a brake on the galaxy's growth. This feedback is a primary reason why the most massive galaxies in the universe are often red and dead, filled with old stars and devoid of the fresh gas needed for new stellar births. This quenching effect is particularly important in the dense urban centers of galaxy clusters. In these environments where galaxies are packed tightly together, a single active black hole in a central galaxy can influence the entire cluster's evolution. Its immense jets can heat the intracluster medium, preventing the catastrophic cooling and runaway star formation that might otherwise occur. In this way, the central black hole acts as a kind of cosmic thermostat for the entire cluster, maintaining a balance and preventing the system from burning through its fuel too quickly. The energy it releases can even create vast bubbles and ripples in the hot gas, visible to X-ray telescopes, which redistribute heat and mix the chemical elements throughout the cluster. This large-scale feedback demonstrates that a black hole's influence is not confined to its host galaxy, but extends throughout the local node of the cosmic web, governing the conditions for thousands of other galaxies. Intriguingly, the scale of a black hole's influence is deeply connected to the properties of its host. Observations have revealed a surprising and tight correlation between the mass of a galaxy's central bulge of stars and the mass of its supermassive black hole. The more massive the galaxy, the more massive its black hole tends to be. This connection suggests that the evolution of a galaxy and its central black hole are fundamentally intertwined, a co-evolution shaped by their shared history of mergers and gas accretion along the cosmic web. It implies that the black hole's feedback is precisely calibrated to the size of its host. A more massive galaxy with a deeper gravitational well requires a more powerful black hole to regulate it. This relationship turns the supermassive black hole from a mere passenger into an integral component of the galaxy's engine, a central governor whose power is directly linked to the scale of the system it helps to control. Through their dual role as gravitational anchors and energetic powerhouses, black holes serve as the ultimate traffic controllers on the cosmic highways, guiding the motion of galaxies, regulating the flow of gas, and determining the pace of growth for entire structures within the ever-evolving web of the universe. But what if the cosmic web we've been mapping and marveling at isn't the entire story? What if our entire universe, with its vast network of dark matter filaments and glittering galaxies, is just one single thread in a far grander, almost unimaginable tapestry? This is the realm of the Multiverse Hypothesis, a speculative but profound idea that pushes the very boundaries of cosmology and forces us to reconsider our place in the totality of existence. It suggests that the specific properties of our cosmic web, the precise strength of gravity, the amount of dark energy, the very rules of physics themselves might not be fundamental, immutable laws, but rather the local bylaws of our particular cosmic neighborhood, one bubble in a frothing sea of infinite universes. This mind-bending concept finds one of its most compelling origins in the theory of eternal inflation, a refinement of the cosmic inflation model that gave us the seeds for the cosmic web. The idea, championed by physicists like Andrei Linde, proposes that the inflationary expansion that jump-started our universe isn't a one-time event that began and ended. Instead, it might be an endless, ongoing process. In this view, the fabric of spacetime is like a constantly boiling pot of water. Most of the water is the inflating background, expanding at a fantastic rate. But every so often, a bubble forms in this boiling foam, a region where inflation randomly stops. When that happens, the energy driving inflation is released in a cataclysmic flash, filling that bubble with hot matter and radiation, and creating what we would call a Big Bang and a new universe. Crucially, each of these bubble universes could have wildly different physical properties. The constants of nature, the strength of forces, the mass of particles, could be randomly set to different values as each bubble forms. In most of these universes, the numbers might be wrong for life or even for structure. Perhaps gravity is too weak to pull matter together, or dark energy is so strong it rips everything apart instantly. But in a rare subset like ours, the numbers are just right or fine-tuned, allowing for the gradual gravitational construction of a vast cosmic web and the eventual emergence of beings who can observe it. String theory, a leading contender for a theory of everything, offers another pathway to the multiverse, painting a picture of existence with far more dimensions than the four we experience. This framework suggests that our entire universe might be a three-dimensional membrane, or brain, floating in a higher dimensional space, like a single slice of bread in a multidimensional loaf. Other brains, other universes, could be floating just a millimeter away in this higher dimension, completely invisible to us because all the particles and forces we know of are stuck to our own brain. Yet, gravity might be able to leak between these brains. A fascinating proposal is that the gravitational pull we attribute to dark matter in our universe could actually be the subtle tug of matter residing on a nearby brain in this higher dimensional bulk. Even more dramatically, some models suggest that the Big Bang itself was the result of a collision between two such brains, a cataclysmic event in a higher dimension that set our entire cosmic story in motion. In this view, the cosmic web structure might bear the imprint of that primordial collision, or the ongoing, ghostly influence of our unseen neighbors. While these ideas are currently untestable and may forever remain in the realm of theoretical speculation, they carry immense philosophical weight. They challenge the Copernican principle that we do not occupy a special place in the universe by taking it to its ultimate conclusion. Perhaps we don't even occupy a special universe. The fact that our universe appears so finely tuned for complexity and life, a fact that has puzzled scientists and philosophers for decades, could simply be an observational selection effect. We find ourselves in a universe capable of producing us, so of course we observe conditions that allow for our existence. In an infinite multiverse, every possible outcome happens somewhere. We just happen to be in one of the bubbles where galaxies could form along dark matter highways, leading to planets and life and curious minds. This doesn't provide a traditional scientific explanation, but it does reframe the question from why are the constants so perfect to what is the mechanism that generates the diversity of constants. The multiverse hypothesis, for all its abstraction, ultimately expands the context of cosmic connectivity in the most profound way possible. It asks us to consider that the gravity-warped highways we've been exploring might not be universal truths, but simply the particular, contingent pathways of our local cosmos. The filaments that connect galaxies may be just one possible expression of how matter organizes itself, one pattern in an infinite quilt of reality. It is a staggering reminder that the pursuit of knowledge, of mapping the cosmic web from the CMB to the Great Walls, is not just about understanding our own universe, but about potentially glimpsing the rules of a much larger meta-reality. While we may never have direct evidence for other universes, the very act of contemplating them deepens our curiosity and underscores the breathtaking possibilities that lie hidden within the laws of physics, waiting for a future generation of thinkers to unravel. This brings us to a question that is as profound as it is personal. Why does this cosmic web, with its specific set of rules and properties, seem so perfectly arranged to allow for our existence? This isn't about a divine plan, but rather a fascinating logical principle that forces us to consider our own place in the cosmos. It's called the Anthropocene Principle, and in its simplest form, it suggests that the universe we observe must be compatible with the existence of observers. As physicist Brandon Carter, who coined the term, put it, what we can expect to observe must be restricted by the conditions necessary for our presence as observers. We are not passive witnesses to a random universe, we are products of it, and the very fact that we are here to ponder it tells us something fundamental about the cosmos's architecture. Think about the delicate balance required for life as we know it. If the force of gravity were even slightly stronger, the cosmic web would have collapsed back in on itself long ago, with matter crunching together in a premature end to the universe. If gravity were weaker, the initial density fluctuations from the Big Bang would never have been amplified enough to form galaxies at all. Matter would have simply drifted apart into a featureless, expanding mist. The cosmic web exists in a gravitational sweet spot. Its filamentary structure is not just a beautiful pattern, it is a functional, life-enabling architecture. The web's specific density and scale ensure that matter can gather into galaxies, but not so quickly and violently that it all ends in chaos. Within those galaxies, the gravitational environment is stable enough over billions of years for solar systems to form and for planets to settle into stable orbits around their stars, providing the long-term, stable environments necessary for life to slowly evolve and thrive. This stability is particularly evident in the safe havens provided by galaxy clusters and their surrounding filaments. While the cores of massive clusters are violent environments where galaxies are stripped and shredded, the outer regions and the filaments themselves offer a far more serene setting. A galaxy like our Milky Way resides in a relatively quiet suburban filament, not in a dense urban cluster core. This location has been crucial. It has allowed our galaxy to evolve without constant catastrophic interruptions, accreting gas at a steady pace to form generations of stars without having its star-forming fuel violently torn away. Our position within the Laniakea supercluster, but far from its chaotic center near the Great Attractor, has granted us a cosmic privilege, a stable galactic home with a long, quiet history, which was an essential prerequisite for life to eventually emerge on a small, rocky planet. Furthermore, the cosmic web is the universe's great recycling and distribution system for the very elements that make life possible. The carbon in our cells, the oxygen we breathe, the iron in our blood, none of these elements were forged in the Big Bang. They were created in the nuclear furnaces of massive stars and then scattered across the cosmos in violent supernova explosions. But that scattering needed a delivery mechanism. The gravitational highways of the cosmic web are that mechanism. These explosions enrich the intergalactic medium with heavy elements, and the flows along the filaments then distribute this enriched material far and wide, seeding future generations of stars and planets with the necessary ingredients for complexity. Without this large-scale circulation, these crucial elements would remain locked in isolated pockets. The web ensures that the products of stellar life and death are shared, mixing the chemical legacy of countless stars across galaxies and eventually depositing them into nascent solar systems like our own. Perhaps the most critical balance of all is the one being played out on the largest scale, between the inward pull of gravity that builds the web and the outward push of dark energy that is now stretching it. For most of the universe's history, gravity was the dominant force, allowing the time needed for the cosmic web to form, for galaxies to evolve, and for stars to produce heavy elements. Now, dark energy has taken over, but its onset was late enough that life had a chance to arise. If dark energy had dominated too early, the universe would have expanded too rapidly for any galaxies or stars to ever form. We exist in a brief cosmic epoch, a golden window where the universe is old enough to have produced the necessary elements, yet young enough that stars still shine and provide energy. The specific values of the fundamental constants, the strength of gravity, the mass of the electron, the cosmological constant, appear exquisitely fine-tuned to allow for this possibility. The Anthropocene Principle suggests that in a vast multiverse of possibilities, we inevitably find ourselves in a universe where the numbers add up correctly. The architecture of our cosmic web, therefore, is not an accident we observe, but a necessity for our own observation. It is the only kind of universe we could possibly call home. Yet, even within the grand tapestry of the cosmic web, there exist structures so immense they defy easy comprehension, pushing our very understanding of cosmic evolution to its breaking point. We call these behemoths Great Walls, and they represent the absolute upper limit of how matter can organize itself under the influence of gravity. The most famous of these is the Sloan Great Wall, a staggering filamentary complex discovered in 2003 from data gathered by the Sloan Digital Sky Survey. To call it a wall is almost an understatement. It is a gravitational continent, a sprawling network of interconnected galaxy clusters and filaments that stretches for over 1.4 billion light-years across the cosmos. To put that incomprehensible scale into perspective, if you could travel at the speed of light, a beam leaving one end of this structure would take over 1,400,000,000 years to reach the other side. Within that mind-numbing volume of space, it contains countless thousands of galaxies, all bound together in a single, coherent structure by the relentless pull of gravity, forming the largest known single entity in the entire observable universe. The existence of such a colossus was profoundly surprising to cosmologists, as renowned astronomer J. Richard Gott III, who has extensively studied these large-scale structures, noted these walls push the limits of what we thought possible. The prevailing models of cosmic evolution, based on our understanding of dark matter and dark energy, had predicted an upper limit to the size of structures. The theory suggested that the initial conditions from the Big Bang, combined with the smoothing effect of dark energy's expansion, should prevent matter from clustering on such an enormous scale. The Sloan Great Wall and other structures like it, such as the Hercules Corona Borealis Great Wall discovered in gamma-ray surveys, challenged those models head-on. Their sheer size and coherence seem to violate what is known as the cosmological principle, a foundational idea that states that on sufficiently large scales, the universe should appear roughly uniform and homogeneous no matter where you look. Finding structures that are not just large but this large forced a major rethink, suggesting that either our models of the initial conditions of the universe were incomplete, or that dark energy's influence on suppressing large-scale structure growth is weaker than we believed. So how does something of this magnitude even form? The answer, as with all structures in the cosmos, begins with the tiniest of seeds in the earliest moments of time. The minuscule quantum fluctuations imprinted in the fabric of spacetime during the inflationary epoch created a spectrum of density variations. Most of these were small, but statistical probability dictates that a few rare fluctuations would be exceptionally large. These became the rarest of cosmic lottery winners' immense overdensities that served as the gravitational anchors for future superstructures. Over billions of years, gravity acted as the great amplifier on these massive seeds. The dark matter scaffolding formed first, creating a vast gravitational watershed of unprecedented size. Ordinary matter then followed this blueprint, flowing along these predefined dark matter highways and gathering at the intersections. What we see as the Sloan Great Wall is not a solid, physical barrier but the densest part of this cosmic watershed, the highest ridge in a gravitational landscape of continental proportions, where the flow of matter from millions of light-years around has been funneled into a single, immense network. The discovery and continued study of these great walls have a profound impact on our cosmological models. They serve as critical stress tests for our most sophisticated supercomputer simulations of the universe. When scientists run a simulation like Illustris TNG or UCHU, they input the known laws of physics and the estimated amounts of dark matter and dark energy, and then let the virtual cosmos evolve. The question is, do these digital universes spontaneously form structures as large as the Sloan Great Wall? The answer helps cosmologists refine the parameters of their models, particularly the exact nature of the initial power spectrum from inflation and the precise strength of dark energy. If a simulation never produces anything this large, it might be because the model suppresses large-scale growth too aggressively. The existence of these walls tells us that the universe is slightly more lumpy and structured on the very largest scales than we had previously anticipated, a crucial data point for understanding the complete history of cosmic evolution. This naturally leads to an exciting and ongoing quest, the search for even larger structures, with ever more ambitious sky surveys like the Dark Energy Spectroscopic Instrument, or DESI, which is mapping tens of millions of galaxies. Astronomers are probing larger volumes of the universe than ever before. The question of whether there is a fundamental upper size limit to cosmic structures remains open. Could there be a wall even larger than Sloan, perhaps so vast that it spans a significant fraction of the observable universe itself? Some tantalizing candidates have been proposed, like the unimaginably large Hercules Corona Borealis Great Wall, though its exact size and coherence are still debated among researchers. Each new map of the cosmos brings the potential for another record-breaking discovery, another gravitational leviathan that challenges our theories and expands our comprehension of what is possible. Ultimately, what these colossal walls reveal is the astonishing efficiency and reach of gravitational connectivity. They demonstrate that gravity's influence is not limited to local groups or even massive clusters. It can orchestrate the motion of matter across billions of light-years, weaving together galaxies and clusters separated by unimaginable voids into a single, cohesive structure. The Great Walls are the ultimate expression of the cosmic web, the final, largest pattern in the universe's grand design. They show us that gravity's highways are not just local roads connecting neighboring towns. They are intercontinental freeways, binding together the entire observable universe into a complex, hierarchical, and deeply interconnected whole. Their discovery reminds us that for all we have learned, the cosmos still holds wonders of scale and complexity that continue to humble and inspire our search for understanding. Now, let's shift our focus from the vast, sweeping architecture of the cosmic web down to the realm of the infinitesimally small, to a ghostly particle that plays a surprisingly significant role in shaping the universe's largest structures. We've talked about dark matter as the primary architect and dark energy as the future destroyer, but there is another, far more subtle actor in this cosmic play, the neutrino. Born in unimaginable numbers during the first second after the Big Bang, these nearly massless particles have been streaming through the universe ever since, and their ethereal passage has left a faint but detectable imprint on the very formation of the gravitational highways we've been exploring. To understand their influence, we first have to appreciate just how strange these particles are. Neutrinos are the cosmic ghosts, the ultimate introverts of the particle world. They are produced in nuclear reactions, from the heart of the sun to the violent explosions of supernova, but most were forged in the fireball of the Big Bang itself. Trillions of them are passing through your body every second, leaving absolutely no trace because they so rarely interact with anything. They have a tiny, almost negligible mass, and for a long time, physicists thought they had no mass at all, traveling at the speed of light. We now know they do have mass, but it is so small that it places them in a unique category, giving them a bizarre property that is key to their cosmic role. They are neither fast enough to completely escape gravity's pull like light, nor slow enough to be immediately captured by it like dark matter. They exist in a gravitational gray area. This unique status dictates their behavior in the early universe. Immediately after the Big Bang, the cosmos was a hot, dense soup of particles. Heavier particles like dark matter and protons were moving relatively slowly, able to clump together under their own gravity. But neutrinos, born with extremely high energy, were moving at nearly the speed of light. This incredible velocity gave them a property physicists call free streaming. They didn't clump or collect, they simply flew in straight lines, effectively smearing out any incipient structures that were trying to form on the smallest scales. As cosmologist Julian Leskurgs explains, this effect means that neutrinos smooth out the web's smallest scales. Imagine trying to draw a fine, detailed pattern in sand, but a constant, gentle wind is blowing across it. The wind doesn't erase the entire pattern, but it blurs the sharpest, smallest lines. That's what neutrinos did to the infant cosmos. They suppressed the formation of the tiniest dwarf galaxies and the thinnest, most delicate tendrils of the cosmic web, ensuring that the first structures to form were on a slightly larger, more robust scale. Over billions of years, as the universe expanded and cooled, these neutrinos lost energy and began to slow down. As their velocity decreased, they started to behave more like other matter, beginning to be influenced by, and in turn influence, the gravitational field. While their individual mass is minuscule, their collective contribution is meaningful because there are so many of them, billions for every proton in the universe. This means they add to the overall gravitational budget, contributing to the total mass that shapes the cosmic web. However, their impact is still incredibly subtle compared to the overwhelming dominance of dark matter. If dark matter is the civil engineer who designed the interstate system, and baryonic matter is the asphalt and traffic, then neutrinos are like a faint, persistent breeze that slightly alters the erosion patterns on the roadside, a tiny but measurable effect on the overall landscape. This subtle influence is not just theoretical, it provides a powerful tool for science. The specific way that neutrinos dampened small-scale structure in the early universe is directly tied to their mass. By using incredibly precise maps of the cosmos today, like those from the Planck satellite that measured the cosmic microwave background, or from galaxy surveys like DAISY cosmologists can look for that specific smoothing effect. They can analyze the statistical distribution of galaxies and clusters, searching for a telltale lack of structure on the smallest scales. The data tells them that the cosmic web isn't quite as lumpy as it would be if neutrinos were completely massless. By measuring this lack of lumpiness, they can actually place an upper limit on the sum of the masses of all three types of neutrinos. This is a stunning achievement. By studying the largest structures in the universe, we can constrain the properties of some of the smallest known particles. The current cosmological data suggests that the total mass of neutrinos is only about 1,000,000 times less than the mass of an electron, an almost inconceivably small value that is nonetheless crucial for our complete physical model. The quest to pin down the exact properties of neutrinos is now a major frontier in both cosmology and particle physics. Giant detectors buried deep underground, like Supermassive and in Japan, and the upcoming Deep Underground Neutrino experiment in the United States, are designed to catch these elusive particles and study their properties directly. They are trying to answer fundamental questions. What are their exact masses? Do neutrinos and antineutrinos behave differently? The answers to these questions will then feed back into our cosmological models, allowing us to run even more precise simulations of the universe's evolution. By understanding the neutrino's role, we can better separate its effects from those of dark matter and dark energy, leading to a cleaner, more accurate picture of what exactly built the cosmic web and how it will evolve in the eons to come. This particle-level interaction, this dialogue between the quantum world and the cosmos at its grandest scale, adds a beautiful layer of nuance to our understanding, proving that to truly grasp the gravity-warped highways of space, we must listen to the whispers of its smallest inhabitants. Yet if we could rewind the cosmic clock and travel back to the universe's infancy, we would find a cosmic web almost unrecognizable from the one we see today. In the first few 100 million years after the Big Bang, the the universe was a much smaller, denser, and far more interconnected place. The dark matter scaffolding had already formed, tracing out a delicate network of filaments and nodes from the primordial density fluctuations, but the spaces between them were not the vast, empty voids we see now. The entire structure was more compact, like a sponge with smaller holes, and the gravitational tides were far stronger, pulling matter together more aggressively. Within these dense, narrow filaments, the very first proto-galaxies began to coalesce, brilliant but isolated beacons of light in an otherwise dark, neutral cosmos. This was a time of rapid construction, where the gravitational highways were being paved at a furious pace, funneling gas into the first growing hubs of matter at a rate the modern, expanded universe could never match. A pivotal turning point in this early story was the epoch of re-ionization, a universal upheaval that fundamentally altered the properties of the gas flowing through the cosmic web. For its first several hundred million years, the universe was filled with a fog of neutral hydrogen gas that absorbed ultraviolet light, making it opaque. But then, the first massive stars and galaxies ignited, and their intense radiation began to burn away this fog. These first sources of light flooded the intergalactic medium with energetic photons that stripped electrons from the hydrogen atoms, ionizing the gas and making the universe transparent. This wasn't a gentle process, it was a violent and uneven transformation. Vast bubbles of ionized gas blossomed around the first galaxies and active black holes, eventually overlapping to fill all of space. This re-ionization heated the remaining gas throughout the cosmic web, raising its temperature from a few tens of thousands of degrees to over 100,000 degrees. This heating had a profound impact on the web's smaller structures. The increased thermal pressure made it much harder for low-mass galaxies to pull in and hold onto fresh gas, effectively suppressing the formation of the smallest dwarf galaxies and forever altering the demographics of the universe. The cosmic web didn't just provide the stage for this revolution. Its filaments channeled the radiation that powered it, acting as the conduits for the energy that changed the state of the entire cosmos. To peer back into these ancient times and witness the web in its youth, astronomers are developing a new generation of extraordinary telescopes. While current observatories like Hubble have given us stunning snapshots of the early universe, they primarily see the individual galaxies, the bright cities, but not the faint, gaseous roads connecting them. The upcoming James Webb Space Telescope is already beginning to change that, using its powerful infrared eyes to detect the faint glow of the first galaxies, and perhaps even see how they align along the earliest filaments. But the real game changer will be enormous radio telescope arrays like the Square Kilometre Array. By mapping the distribution of neutral hydrogen across billions of light years, these instruments will act as cosmic magnetic resonance imaging machines, tracing the faint outline of the primordial web itself. They will create three-dimensional maps of the gas within the filaments during the epoch of re-ionization, showing us how the first structures funneled material and energy, effectively allowing us to watch the universe turn on its lights for the first time. These are not just telescopes, they are time machines designed to capture the universe's childhood and show us the first draft of the gravitational blueprint we live within today. For clues about the web's history that are much closer to home, we can look to ancient time capsules orbiting our own galaxy globular clusters. These are dense, spherical swarms of hundreds of thousands of stars, all bound together by gravity. They are among the oldest known objects in the universe, having formed when the Milky Way itself was just assembling, over 13 billion years ago. Crucially, their stars are pristine. They formed from gas that had been enriched by only the very first generations of stars. By studying the chemical composition of these stars, astronomers can perform a kind of cosmic archaeology, reading the conditions of the early cosmic web imprinted in their elemental abundances. The fact that these clusters exist at all tells us that the web was already capable of creating incredibly dense knots of matter very quickly after the Big Bang. Their motions around our galaxy also preserve a memory of the Milky Way's own violent growth. Many clusters were likely originally the cores of small dwarf galaxies that were cannibalized by the growing Milky Way long ago, their stars stripped away and absorbed, leaving only their dense hearts behind as fossils of past mergers. Each globular cluster is a relic from a more chaotic, interconnected time, a living witness to the era when our local patch of the cosmic web was still under construction. But this era of vibrant connectivity is, from a cosmic perspective, only a temporary phase. The same force that illuminated the universe, dark energy, is now orchestrating its gradual isolation. As the accelerated expansion continues, the future of the cosmic web is one of increasing dissolution. The great filaments, those rivers of galaxies and dark matter, will be stretched ever longer and thinner. The gravitational currents that flow along them will weaken as the distances between mass concentrations become too vast for gravity to effectively bridge. Galaxy clusters will continue to grow through mergers for a time, vacuuming up the last galaxies flowing along the fading filaments, but eventually even that inflow will cease. The clusters will become isolated islands in an ever-growing sea of expanding nothingness. Billions of years from now, an observer in what was once the Milky Way would look out into a profoundly dark sky. All other galaxy clusters, carried away by the accelerating expansion, would have been redshifted beyond the visible horizon. Their light, stretched to wavelengths longer than the size of the observable universe itself, would simply never reach us. The universe would appear as a single, giant galaxy adrift in an absolute blackness, with no external clues to suggest there had ever been anything else. The grand cosmic web, the great connector of all galactic life, will have faded into memory, its highways stretched and severed by the relentless push of dark energy, leaving behind a cosmos that is cold, dark, and profoundly alone. This profound understanding of our interconnected cosmos does more than just satisfy scientific curiosity. It invites a deeper, almost philosophical reflection on what it means to be part of such a vast and intricate system. For centuries, human philosophy grappled with questions of isolation and purpose, often seeing the universe as a cold, empty void. But the revelation of the cosmic web completely upends that view. It presents a universe that is fundamentally relational, where every galaxy, star, and planet is in a silent, constant dialogue, linked by the invisible threads of gravity across the deepest voids. This isn't just a network, it's a universe that is woven together, a single, dynamic entity of which we are an infinitesimal but integral part. This shift in perspective, from a universe of isolated objects to a universe of dynamic connections, is one of the most significant contributions of modern cosmology to human thought. This idea of a connected cosmos has been beautifully articulated by some of science's greatest communicators. Carl Sagan's famous declaration that we are made of star stuff was more than just a poetic turn of phrase. It was a radical statement of physical kinship. He wasn't speaking metaphorically. The carbon in our DNA, the oxygen we breathe, the iron in our blood, these elements were forged in the hearts of long-dead stars and then scattered across the galaxy by supernova explosions. That material was then gathered up by the gravitational currents of the cosmic web, funneled into a new generation of stars and planets, and eventually found its way into us. This means the cosmic web isn't just something out there that we observe. It is the very mechanism that delivered the building blocks of life to our solar system. We are not just observers of the cosmic web, we are a product of it, a local manifestation of its large-scale flows. This realization creates a powerful sense of belonging, situating our personal story within the grandest narrative possible. This new cosmic imagery has also had a profound cultural impact, reshaping how we visualize our place in existence. The classic image of Earth as a lonely blue marble floating in black space has been replaced by a more nuanced vision. Our pale blue dot is situated within a local stellar neighborhood, which is embedded within a galactic disk, which is itself flowing along a specific filament of the vast Laniakea supercluster. Art and science fiction have eagerly embraced this iconography. Visualizations of the cosmic web, with its brilliant nodes and glowing filaments set against a backdrop of dark matter, have become some of the most iconic images in modern science, rivaling the pillars of creation or the Hubble Deep Field. They provide a new mental model for the universe, one that emphasizes relationship and process over isolation and permanence. This imagery helps us internalize the science, making the abstract mathematics of cosmology feel tangible and real. It allows us to literally picture ourselves within the grand architecture of everything. The language we use to describe this structure is itself powerful. Metaphors of highways, rivers, skeletons, and webs are not merely decorative, they are essential tools for comprehension. They allow us to take a concept that is utterly alien to our everyday experience, the gravitational influence of dark matter over billions of years, and frame it in terms we can intuitively grasp. Speaking of galactic cannibalism or cosmic recycling does more than just simplify, it creates a narrative. It tells a story of a universe that is evolving, competing, cooperating, and recycling itself across deep time. This narrative framework is crucial for public engagement with science. It transforms a list of facts into a compelling saga, inviting everyone to become a part of the story of discovery. These connectivity metaphors make the science accessible, but they also shape how we think about the universe, encouraging a more holistic and ecological perspective where everything has a role to play in a larger, interconnected system. This expanded view of a connected universe inevitably brings with it a sense of ethical consideration. Contemplating such immense scales of space and time can be simultaneously humbling and empowering. It highlights the incredible rarity and fragility of our planet, the only known oasis of life in a cosmos that is largely hostile to it. This perspective, often called the overview effect experienced by astronauts, fosters a sense of planetary stewardship. If everything is connected, then our actions on this small world ripple through a single, interconnected biosphere. Furthermore, the vastness of the cosmic web puts our human conflicts and divisions into a starkly sobering context. All of human history has played out on a speck of dust adrift in a single galaxy, which is itself just one tiny strand in an immeasurable web. This isn't meant to diminish our existence, but to broaden our perspective, suggesting that our greatest challenges require a unified, species-wide response rooted in our shared origin among the stars. Ultimately, the greatest lesson of cosmic connectivity is about the nature of curiosity itself. The fact that a species on a small planet orbiting an average star has been able to deduce the existence of dark matter, map the large-scale structure of the universe, and trace its evolution over billions of years is a testament to the human drive to understand. We used our own innate intelligence to uncover the hidden architecture of the cosmos, and in doing so, we discovered that we are physically woven into that same architecture. The universe has evolved the capacity to understand itself through us. This creates a beautiful loop of meaning. Our curiosity is not separate from the universe. It is the universe becoming self-aware, contemplating its own origins and its own astonishingly beautiful structure. The gravity-warped highways of space connect galaxies, but they also connect us to a profound story of emergence and evolution, inviting us to continue looking up and wondering, not as separate observers, but as the universe itself, beginning to comprehend its own incredible nature. The gravity-warped highways of space reveal a universe far more interconnected than we ever imagined. A cosmos where galaxies are not isolated islands but vibrant communities in constant, silent conversation across billions of light years. This grand dialogue is orchestrated by the subtle, relentless pull of gravity and the pervasive flow of dark matter, weaving together everything from the smallest dwarf galaxies to the largest superclusters into a single, dynamic tapestry. We've journeyed together from the immense filaments of the cosmic web, those great rivers of dark matter and gas, to the enigmatic force of dark energy, which now stretches this entire architecture, dictating its ultimate fate. These hidden pathways are not mere backdrops, they are active participants in the story of everything, shaping how galaxies are born, how they evolve through dramatic collisions, and how they eventually fade, all while guiding the very distribution of the elemental ingredients necessary for life itself. Our exploration has shown that to understand the cosmos is to appreciate its profound connectivity. The same gravitational currents that funnel galaxies toward the Great Attractor also once delivered the enriched gas that formed our solar system. The dark matter scaffolding that defines the web's structure also protected the early universe from flying apart before stars could even ignite. And the dark energy now accelerating the expansion ensures that this golden age of structure and discovery is but a fleeting, brilliant phase in a much longer cosmic story. As our telescopes and simulations grow ever more powerful, allowing us to map these structures with increasing precision, we are doing more than just solving astronomical mysteries. We are piecing together our own origin story within this vast, evolving network. Each new map of the cosmic web deepens our awe for the universe's grandeur and complexity, revealing a reality that is stranger, more beautiful, and more interconnected than we could have ever dreamed. So the next time you find yourself under a clear night sky, away from the city lights, take a moment to truly look up. Those points of light are not just random specks. You are gazing out along the local arm of a vast gravitational highway, glimpsing our nearest neighbors in the immense flow of the Laniakea supercluster. You are seeing the visible evidence of a hidden architecture that binds the entire universe together. That simple act of looking up and wondering is a testament to a profound truth. Our curiosity is the universe's way of beginning to understand itself. This journey through cosmic connectivity reminds us that we are not just observers of the cosmos. We are a product of its intricate, dynamic web, and our quest to unravel its secrets is one of the most beautiful and meaningful